Can you hear me?
Yes. Yeah.
So I'll share the
Yes.
screen.
Yes.
Okay. Hi, good morning, everybody. So we are just getting set up. Just a minute.
Dr. Panda and Hari, I'll give a quick intro and then you can take
Sure.
over.
Sure.
Yeah, definitely. Just a minute. Do people see me in the Zoom or not?
Yeah, we can see.
Yeah.
Yeah. Okay. So then why it is asking me again join or something is in progress? Okay. 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 Can you see my screen now?
Yes.
Yeah.
But not in the presentation mode, am I right?
No.
How about now?
No.
No?
No.
Okay, let me try again. How about now?
No.
Still no. Yeah, we are seeing the presentation, but not the slideshow.
Yeah, okay. So I'm sharing the window or okay. Now you see the slides?
No, still I see the slides, but not in the presentation mode.
How about now?
Same.
So what is happening? Here I'm able to
go to slideshow, Dr. Prana. This slideshow.
Go to slideshow. Okay.
And
from the beginning. Yeah.
No. So you need to change the monitor that you see under accessibility reminder. So primary monitor. Try the other.
Okay.
Monitor.
Okay. Automatic.
No. Yeah.
Is it better?
No, but try now.
Yeah.
So how about this? Let me share it on my screen, and you can. I'll give you control of my screen.
Okay. Sorry, guys. I had my laptop crashed. I have a loaner laptop, so everything is new on this thing. So
yeah, Hari, we can see. I think.
Yeah, go ahead, Dr. Panda. You should have remote control of my screen now. You can go ahead and present.
Yeah. So let me give a quick intro, and then you can take over.
Okay.
Hello, everyone. Welcome to the tutorial session today at Hot Interconnects. We had 2 days of great keynotes and talks. Today is the tutorial, and there are total 6 tutorial sessions which were spread over like 2 tracks. We are right now in track 1, which has like introduction to network technologies for HPC, and followed by in the afternoon high performance machine learning, deep learning, and data science. In the track 2, which starts at 9 a.m. PT time, it has 4 topics. You can look at the hot tea Hot Interconnects webpage for the details on the track 2. It's my pleasure to introduce the speakers for the first session. Professor D.K. Panda is a professor of computer science and engineering and university distinguished scholar at Ohio State University. His research interests include parallel computer architecture, high performance networking, exascale computing, big data, deep learning, programming models, accelerators, high performance file systems and storage, virtualization and cloud computing. He has published over 500 papers in major journals and international conferences. Professor Panda and his research group members have been doing extensive research on modern network technologies, including InfiniBand, high-speed Ethernet, RDMA over converged enhanced Ethernet, RoCE, Omni-Path, and EFA. Dr. Panda and his team has been actively working on these well-known MPA libraries, MVAPH, and the PGAS libraries, and more recently on the deep learning libraries and big data libraries. Dr. Panda has served as program committees on several international conferences. He's an IEEE fellow and a member of ACM. And the other speaker we have for this session is Dr. Hari Subramoni. Hari received his PhD degree in computer science from Ohio State University in 2013. He is a research scientist in the Department of Computer Science and Engineering at Ohio State University since 2015. His research interests include high-performance interconnects and protocols, parallel computer architecture, network-based computing, and exascale computing. He has over 70 papers in international journals and conferences related to these research areas. He has been actively involved in various professional activities in academic journals and conferences. His current research focus is primarily on MVAPH2 and MVAPH2X software packages. Yeah, over to you, Dr. Panda.
Okay. Thanks a lot, Sudhir, for the kind introduction, and welcome everybody to this tutorial which Hari and I'll be presenting. And just a minor update, Hari is actually now an assistant professor in the computer science department. So I think the bio was a little bit older one. So the way we'll proceed here is we'll go with the might be before we get started, if a few of you can just introduce yourself, tell us a little bit about what you would like to learn from this tutorial, give a little bit of background. We have 4 hours, we'll have a little bit of break in between, but then we can know you very well and then present things in an appropriate manner. Any volunteers?
Saurav, would it be possible to allow the audience to, let's say, unmute themselves if they want to?
I think Saurabh is muted. Or if at least, okay, so you are posting in the chat. So Suresh Singh from Aerospace Corporation, thanks, nice meeting you. People can also post questions in the chat also. Okay, good, you are an HPC administrator, that's nice. Anybody else would like to introduce? Okay, if not, let's get started. And so Hari, I'm just trying to check is the slides moving? I don't.
Can you try now? Did you accept? So you need to accept the remote control. Did you accept it?
No, it says it doesn't. It just tells me I get a message saying you can control Hari Subramoni's screen.
Yeah.
Give up remote control, but no other message came. Can you
try to click somewhere?
Okay.
Oh,
request remote control. Okay.
Okay. So can you try? Oh, sorry. Hold on. Can you request again, Dr. Panda, please?
Okay.
Yeah. Can you move now?
No, it is.
Yeah, you are moving. I think you are moving now. Yeah, you are moving now. Yes.
Yeah, okay, so this one is moving, but the slide, if I go to the next one, I think.
Yeah.
If I okay. Yeah, it's a little bit slower. That's fine. Okay, so then let's get started. As we see here, I think the slides are available. Please feel free to download this, and might be Hari, you can post it on the chat also.
Yeah, I have
For
posted
everybody.
on Slack.
Okay. So the whole idea what we'll be talking is like the introduction to networking technologies for high performance computing. As you know, the HPC field is moving very rapidly, and a lot of excitements are happening. And we want to provide you like a comprehensive perspective of the state of the art here. So the outline will be as follows. We'll start with a high level introduction, then give a little bit of historical perspective, like what has happened in the 30-40 years, why high performance networking, people have been thinking, what are the bottlenecks, and how this field has evolved over the years. Then we'll discuss about communication models and semantics of high performance networks. So when you are trying to design a network, of course, some other software on top of it, it could be an MPI, or it could be a file system, it could be a cloud, some other software stack is actually interacting with that network through the adapter and then going through the switches. So we'll first spend some time understanding that, because once you understand that communication model and how software people have been developing these interfaces, then we can go and try to take a look at the networking technologies. So obviously, as you can see here, I mean, there are a lot of different networking technologies: Infiniband, high-speed Ethernet, the convergence, which is Rocky, Omni-Path, NVLink, Amazon EFA, Clay Slingshot, Fujitsu Tofu, Google Aquila. Some of them are proprietary, and then some of them are commodity. So we'll start with the commodity ones, like especially Infiniband, high-speed Ethernet. They have been there for many years. And once we understand all the details there, then we'll gradually try to take a look at the other ones and see the differences. Okay. So then you will get, we'll not have time to really go and uh, go into all the features of all the networks, because we only have half a day. So once we understand all these networks, then we'll go into the software stacks, because as I just said earlier, um, I mean, you might have the great hardware, but if the software interface is not there, I mean, you cannot really utilize it in your environment. So here we'll take a look at some of the software stacks, again, going back to a little bit in the history, like Open Fabrics, how it is evolving, UCX, Leaf Fabric. So these are the kind of 3 software stacks we'll be talking. And then we'll give you a little bit of perspective of sample case studies and performance numbers. If you are totally new, you might have been exposed to all of these, but how about the performance? So that's what we'll try to, we have taken some numbers in our lab, and then we'll be able to share those numbers. And then towards the later part, we have a lot of very nice hands-on exercises. So if you are totally new, we have at least the Infiniband cluster here locally in my lab. So we have actually accounts. So we'll go into all those details. You can get a guest account, and then you'll be able to actually run some experiments. So that will be kind of the second part. So we have 4 hours here. Broadly the way I am thinking, we can go for 1.5 hours, 12:30 Eastern and 9:30 Pacific. Might be we'll take a 15 minutes break, and then from that break, so what happened?
Sorry.
Hmm?
My hand touched the.
Oh, sorry. So and then from there. And then we'll take a 15-minute break and then come back and then continue. And at any time, if you have any questions, please feel free to post it in the chat, and then we'll be trying to answer those as we go along. So if you take a very broad look, the big field of high performance computing, it has been we have been seeing the growth in processor performance over many years. In the very early days, if you remember, some of the old timers, the processor speed was increasing, but things have changed because of the power constraints and all. And these days we have chip density doubling every 18 months, so we get more and more number of cores. If you take a look at the latest AMD Milan, it is actually the one chip has 64 cores. So if you put like two chips on a single board or a single server, we have 128 cores. So this kind of density is doubling. And then the question is, how do we build large scale systems out of these? So this is where like there is an increase in speed, features is happening. And in that context, the clusters have become very popular choice. And this is for upgradability, modularity, and then people are trying to handle all these kind of applications, might be a crash dynamics, a nuclear simulation, bioinformatics, etc. So now if you take a look at commodity computing clusters. So clusters are there. Now let me focus a little bit on the commodity aspect. Okay. So this field has been evolving here. These numbers are from top 500. I am sure many of you are familiar with the top 500. It has been there. Like they started in almost 1996, and every year like the top supercomputers get ranked. One in the supercomputing conference in November in US, and then once in June in Germany. So what it's trying to show, these are the timeline, and then we have the number of clusters, and out of those number of clusters, basically the y-axis is out of those 500 systems, how many of your commodity clusters? Okay, commodity in the sense, if you have money, you should be able to go buy a bunch of servers, some kind of network adapter, network switches, get the software from somebody, and then put them together. Okay, so this is very different than, let's say, many years back, some of you might have heard of IBM Blue Gene. So that was not a commodity system, that is a proprietary system. Okay, so that means IBM delivers you this entire thing. You cannot buy a BlueGene adapter or a BlueGene switch from outside. So then what has happened over the years, as you can see, this trend is steadily increasing. And in the very latest one, you will see almost like a 98% of these machines are commodity clusters. Okay, only as you can see in the June, it got dropped. We'll come to that. That is because of the slingshot. Cray, HPE have the slingshot, so that is still not a commodity. I don't think you can just go and buy slingshot adapters and switches from the market. You have to buy the entire system. So here, especially starting from June, we are seeing a little bit difference. But otherwise, as you can see, it has been steadily rising. And of course, in the future, we don't know how these numbers will change. So we'll keep an eye on both the sides. Most of the time we'll say commodity because those are open. We can talk a lot about those, but the other ones are like a closed. So whatever information we have, we'll be able to share those with you. So now if you take a look at very high level, like a integrated high-end computing environments. So of course, we talked about these commodity clusters. Most of the people think that, yeah, I have a cluster in my lab, a bunch of like a 16 nodes, I can put it together with a switch. That is the compute cluster. But if you take a look, the concepts of clustering is used at many other places. It is not only restricted to the computation. So think of like a storage cluster. I mean, these days, a lot of machines are like you try to handle petabytes of data. So if you look at the storage architecture of that system or that subsystem, that itself is also a cluster, because you will get a lot of bunch of nodes connected with some kind of a switches, and then you will have some metadata manager, some of the server nodes. The bigger thing here, if you see at the bottom, is the actually the multi-tier data center. Okay, so think of like a means I'm sure every day we interact with these kind of data centers on a continuous manner, whether you are buying something from Amazon, or you are interacting with your bank or your insurance company, or you are trying to look at some news channel or video channel. Everybody is going through this kind of a multi-tier data center. So let me explain the concept here a little bit. So let's take an example of very simple Amazon. Let's say you are trying to buy something from Amazon. So you say Amazon.com. So basically Amazon has a lot of front-end servers all over, distributed all over the world at all different places. So depending on where you are living, when you say Amazon.com, your request is going to one of these front-end servers or the routers. So then you try to say, okay, I'm searching for this book. So once you search, your request actually goes to the second stage, which is like the app server. So this is where it does the search, and then very quickly you will see a response, like saying, yeah, there are so many copies of these books are available, so many old, so many new. And you also get a lot of other kind of information saying 50% of people who bought book X also purchased book Y and G. So those are the kind of the internal information Amazon provides to you. So you browse all those things, books, or if it is a product, you look at all the pictures, cost, reviews, all those things. And then once you decide to purchase, so then your request gets moved to the next tier. So this is like the database server. It exactly then asks you saying, okay, this is my give me your credit card, the addresses and all those things. And it actually does the transaction here. And then it just says, thank you, your things will be delivered at such and such place. So the response comes back. So this is kind of a very generic, like a 3-tier, but depending on the company, organization, some of them implement in 3, 3.5, 4, 5. Everybody has their own customized design. Okay. But if you take a closer look, these are also very similar to these compute cluster, storage cluster. We have again a bunch of servers. Their functionalities might be different. Might be also the configuration might be a little bit different. Some of them might have more memory. Some of them might have a GPU. Those kind of things. But the broad idea of the commodity cluster is still there. Like we have a bunch of servers connected with some switches. And sometimes you will see there is also an integrated environment. Like if you go to a bank, of course they have a data center where customers like us are actually interacting, but behind the scene they also have their own computational thing or internal computation. They might be running some financial modeling, stock market prediction, all those kind of things are happening in the behind. And these are connected over local area network, wide area network, um, totally geographically distributed, and these are all connected to their storage where their data resides and also the customer data resides. So when we talk about this big thing, we need to, like the cluster computing, networking technologies, we need to keep all these aspects in mind. And if some of you are familiar, I mean, this market is a very big market, the data center market. That market is much more larger than even the HPC small compute market. So when a vendor comes up with some kind of a solution, of course, they want to target it to all these three kind of sub markets. Okay, and that's what we'll see as we go along. And that is those are the on-premise system. And of course, now you see, I mean, there's a lot of focus on the cloud, and the idea is very similar again in the cloud. Whether you go to Azure or IBM or Google, you will see again a bunch of physical machines. So the only difference is that on the on-premise system, you are getting the physical access, and then here you get the virtual machines. So the physical machine might be one or more VMs might be running on that, and same thing also happens with the file system. It's a virtual network file system which you are trying to use. And of course, then you can go into very different application domains. Like let's say you think of like a big data analytics with Hadoop and Spark, very similar ideas. You have a bunch of nodes connected with some kind of switches. Of course, many years back, it used to be traditional Ethernet, but over the years, I mean, people have found out bottleneck and people are using high performance networking even in that context. So, and then of course, the machine learning, deep learning, AI, I mean, all those fields are out there. Now, if you take a look at this big picture, and then let's say you are a networking architect, or if you are a student, or if you are a new person in this community, you want to ask questions saying, what are the networking and IO requirements of all these systems? Okay, so then this is how a set of answers will come. Okay, so the first is like a good system area network with excellent performance. Of course, we are focusing, let's say, high performance computing. Performance is very important. So the question is, how do you define the performance? So there are some metrics. So there have been like a traditionally there have been a metrics like a latency and bandwidth. I think most of you might be familiar. Latency is like if I send some data from one server to the other server, how much time does it take and then return back? Okay, so that is the kind of the half of round trip. You can say it is a one-way latency. Bandwidth between the two servers, we can keep on pumping the messages, and especially this is good for large messages. The higher I can get, it's better being utilized. So that is kind of a bandwidth. So these two metrics used to be there many years back. But then around 20 years back or even 25 years back, a third metric was introduced, and that has a lot of impact as we go on and discuss all the other things. It's called CPU utilization. Okay, so what does that mean, CPU utilization? So this is the CPU utilization not for application, CPU utilization for network processing or network protocol processing, to be very precise. Okay. So let's say I have two products. They have very similar latency and bandwidth, but let's say product A says that in order to carry out network protocol processing is the CPU utilization is 30%, and another one, the B, it says 5%. Which one is better? Any answer? You can post your answer in the chat. %5 one, okay. Why? Any clue? Okay, low overhead. So what it means that in order to carry out the same task, I'm trying to utilize less CPU cycles. So that means I have more CPU cycles left for the actual computation, because these servers, I mean, of course, you have networks for to do network protocol processing, but we have some other higher up applications running on top, and we want to give most of the cycles to the application layer. Okay? So then of course, if I have like a 5%, then my 95% of the CPU cycles are left for computation. But of course, this is good for performance, but then gradually we'll come to the here this question about the cost. Okay, we also need to keep in mind, like there is A and B. B is good for performance, but how expensive is that compared to A? Okay, because that will determine again, like if you are deploying a cluster of 16 nodes versus 16,000 nodes, I mean the answers will be very different. Okay, so we need to keep that big picture. We'll come to that. So then the good storage area networks. We saw several applications where not only we need good communication, we also need good storage. So we need this good storage area network. We also need good wide area network connectivity, in addition to like the SAN and LAN connectivity. And then over the years, there also has been a lot of focus on quality of service. Of course, I mean, many of you, I mean, if you have traveled and all, I mean, like all these airlines these days have all these different kinds of quality of service in terms of like your medallion status. You might be a silver, gold, platinum, diamond. Based on that, you get different kinds of services. Similar kind of things are now happening in commercial entity. For example, Amazon. If you are a very frequent customer of Amazon, they can detect, or you can be promoted into some higher levels, like the Amazon Prime, as you know. Similarly, like Macy's have a scheme, so you can go into the next level, and your request gets solved faster. Okay, so as soon as you log on to the system, it detects that, oh, you are a valued customer and you have this level, so they want to make sure that your request actually get serviced much more faster. So of course you can do it through software, but if the hardware provides some features, designing that software infrastructure becomes easier. So a lot of these modern networks are actually trying to provide those kind of quality of service. And especially those of you who are in the HPC center, you might have always heard a comment saying, oh, there are different jobs, different people are running jobs. Somebody is running a job with very large messages, IO intensive, and then all others are getting affected. Okay, so that is quality of service. So can you actually design quality of service and take it to the even to the MPI layer, the upper layer, so that this the running the big jobs with the IO oriented applications don't affect the other jobs where they're sending small messages. So that's how quality of service is becoming important. Then of course we have the reliability, availability, and serviceability, RAS. This also has been becoming very important over the last almost 20-30 years. If some of the old timers used to be there, you can say that, okay, if you the earlier the traditional idea was that if a machine goes down, we'll fix it in the night. Okay, that used to be the the usual mode of operation. But these days, if you see, there is no concept of night. I mean, if you are an Amazon data center, every day is day, 24/7 by 365, you have to operate. Okay, because people from all over the world are interacting, and many times you would have seen some news articles saying even if a power goes down or a data center goes down, even for a 1 hour, they lose millions of dollars. So that means the system has to be designed from even from the below, from the hardware level, firmware level, so that this kind of RAS exists. built in. So while the system is running, if we detect some fault, you should be able to isolate itself, that particular components, and then move it to the others. Okay. So these are all good, but then the question is, how much does it cost? That's what I indicated earlier. So this is where this commodity networking and all these companies compete with each other. So they have a set of features, but then just like think of like cars. I mean, there are so many different models of car with different features. So as an end consumer, it depends on you which one you want to purchase and what features are good for you, and then of how much you are willing to offer. Okay, and exactly. So this networking market has become very similar to like a buying a refrigerator or buying a microwave versus buying a car or any other kind of a washer dryer. Uh, this market is operating in a similar manner. So with this, let me move to the next one. Uh, Hari, did we lose something here? No, it comes. Okay. So then let's go back to the very basic computer architecture 101. I'm sure all of you know about this. A typical server, if you open up, I mean, the architecture is very similar. It's like your laptop or even a iPad or iPhone. We have a bunch of processors. We have some memories, and then there is an I/O bus. There is a network adapter, and then you connect it to the network switch. So these are some of the fundamental components in any server to build this kind of clusters. Of course, these are the hardware components. There are some software components. So this is where the communication stacks comes in, and then you have to put it on top of that for the system to work. So because of these commodity components, these days, if you see, I mean, um, like let's say you are trying to buy a laptop or a server, you will be seeing like the processor is coming might be from Intel or AMD, memory is coming from might be Samsung or um, uh, any other company. The storage is coming from some other Western Digital. Networking might be coming from Broadcom or NVIDIA or Mellanox, and the switch could be some Ethernet like Arista and all. So if you put it together, at any given point of time, when you are trying to deploy a system and when you are trying to purchase it, there could be different kinds of bottlenecks. Okay, so one is kind of a processing bottlenecks. Okay, so that means this is processing bottlenecks for the network protocol processing. This is not the application level. Okay, so like every time I want to take some data out, how many memory cycles I need to touch. So similarly, then we have I/O interface bottleneck. So this the I/O interface is like connecting your memory to the network adapter. So we'll talk quite a lot of focus on these, like a PCI, PCIX, PCI Express, etc. And then the third bottleneck is the network bottleneck itself. That means even though I have put together the system very good, very well, but the outside network is not very strong. Okay, so then we cannot operate it in a balanced manner. So let's take a little bit of details trying to understand, because that will help us to understand what these high performance networks technologies are trying to do, and what are the features. So we'll be able to correlate all these things. So let's start with processing bottlenecks. So if you remember, I'm sure all of you are familiar with TCP/IP, UDP/IP. These are the generic architectures for all networks. So if you go back to your like a computer networking class, you will see that the TCP/IP has been there. It's a multi-layered protocol. There are signaling between different layers. You try to do some data buffering, data integrity. You take care of the routing, and there are some interrupts on the packet arrival and retransmission. There is some software signaling layer between different layers to handle the protocol processing. So each one of these takes time. Okay, so that's why even though like I'm trying to send some 1 bytes or 2 bytes from this node to the other node, you may see some couple of microseconds. Okay, or even sometimes even it can go to 10 microseconds and all, depending on the hardware and all. Okay, um, because these things keep on adding up. So that is kind of a protocol processing bottleneck we'll see. The next one is the I/O interface bottleneck. So this is sometimes also known as the last mile bottleneck. Okay, and if you remember, especially in the like the two years back with COVID, everybody encountered this. I mean, everybody got changed to Zoom and all. So now it depends on what kind of like, let's say I'm staying at home, how much bandwidth is coming in and out of my apartment or home. That determines how I can interact with the world. The world might have a lot of networking bandwidth, but if I have only like a 10 gigabits connections to my my home, that is the rate at which I can do. Of course, there is an upload rate and the download rate. It depends on that. So same thing exactly happens within the systems. So I have the servers. So depending on this IO interface, I can actually see how I can communicate to the outside world. So in this context, if we go back almost 1990, like almost 30 years back, we this idea was standardized called PCI, okay, peripheral communication interface. So if you go back PCI, it was done with a 1 bit for wire. So it was a kind of a bus, and then in every wire you have so many number of buses, so many number of lines or wires, and in every wire I can send one bit. Okay, so if you do like a quick calculation here, like it used to be a 32-bit bus, and each line is operating at 33 megahertz. So you will see like a 1 gigabits per second, and that is a shared bidirectional. Okay, so that means if I have only a PCI, I cannot go exceed 1.5 gigabits per second. Doesn't matter what kind of network switch I put outside. So then gradually people saw there is a limitation. So so here you can think of like a 2 degrees of parameter, like how many bits I can have and how much speed I have. So then this PCI extended was introduced in 1998 version 1, 2003 version 2. So here they tried to do like a 64 bit. So they widened from 32 bit to 64 bit, and then they increased the speed from 33 megahertz to 133 megahertz. So if you do this, you see like you get 8.5 gigabits per second. Okay, you get a multiplication by like a factor of 2 here and factor of 4 here, 4 times 2. So you get factor of 8 improvements. But then there was even more updates in the version 2 that even doubled. So it kept the bus width same, 64 bits, but it tried to change to 266. So then it was going to 17. If you go to 533, it can go to 34 gigabits per second. But while doing this, if you're familiar with some basic electrical engineering principles, if I have a bus where the lines are very close to each other, and if I'm running them with a very fast speed, there will be a lot of crosstalks. Okay, and there will be bit skews between the wires. So even though I send a lot of data, because of these collisions, a lot of signal integrity will be affected, and the effective bandwidth rate will be very low. And that's what people found out, like around early 2000 or late 90s. People saw that, yeah, that is not the way to keep on increasing. And of course we'll come back to solutions to these problems very soon. And then let's say the third bottleneck, which is the actual network. So assume that you have very good processors, memory, you have an IO bus, and you have a good network adapter. Then the question is, okay, is there a limit to the outside world? Okay, and this is where if you go in the history, 1979, Ethernet started. It had only like a 10 megabits per second. And then first Ethernet started, like, see, almost 14 years, the world was very happy with Ethernet. Okay, because if you go back to that time, I mean, there was no concepts of like a video streaming or doing any high performance computing or in network computing. None of those things were there. It was used to be the Ethernet only used to be used in some defense installations, military. They were sending some messages. That's all. Okay. So the computing load was not there, or the distributed computing, parallel computing, all those concepts are not come. But then gradually, as the field evolved, people saw that, okay, you need more and more network. It is just like the example, if there is a small village, you don't need a freeway. But as the population increases, you will gradually see that I need more street, the street needs to be widened, I need some freeways. Exactly same thing happens here. Okay. So over the years, as the system sizes became larger and larger, every node became faster and faster, there was a lot of demand to in fact to provide faster and faster speed. So then you see with the first Ethernet was 1993. In 2 years, gigabit Ethernet was introduced, like it was the 1000 megabits per second. Then one technology was introduced called ATM. It's not like a bank ATM. It's called asynchronous transfer mode. A lot of ideas from telephony world came to the computer networking. I mean, the telephony has been there for almost 200 years. People have been using telephone, telegraphs, all those kind of things. So there are a lot of ideas. All those things came to the computer networking. It was very active for some time, but then again it died, and then people redefined that terminology called another terrible mistake. Okay, that's what people found out, that ATM died because people are not able to adopt it. But then the real commodity things came, if some of you remember, is 1993, almost like 30 years back. This is where the cluster computing concept started. Okay. There is a technology, there used to be a technology called Mirinet from a company called Miricom. They still exist. They have been purchased by others. But this is where they really had a come up with some adapters and switches. And if you have a bunch of servers, you can actually put them together. And that used to be known as networks of workstations. Okay. If some of you go back, this is how it evolved. So if you have a bunch of servers, that time it used to be Sun, Solaris servers and all. So then you buy the switch. So now your capability increases. If I buy an 8-port switch, or even there, they used to sell 4-port switches. 4-port switches, 4 adapters, plug it to my 4 Solaris server. I have my networks of workstations or network of servers, which is 4. So then, of course, people saw the need in the storage aspect, and this is where the fiber channel came in 1994. So as you can see, these are all like a 1 gigabits per second. So that's how the field evolved over a period of time, and people found out like these kind of bottlenecks. So then we are like in late 1990s, and this is where people started thinking about, can we design or totally come up with new ideas where networks, instead of just being providing a connectivity, we have to bring performance. Okay. And this is the where the idea of high performance networking, or HPN, started. Okay. And people wanted to do industry networking standards. So 2 initiatives were done at that time. And this was like the birth of Infiniband. Okay, we'll go into a little bit more details. And at the same time, Ethernet was there. So they also wanted to redefine it into high-speed Ethernet. So around like 2000, these 2 directions started coming up. And Infiniband, because it was new, it aimed actually to handle all the 3 bottlenecks: protocol processing, IO bus, and as well as networking speed. But the Ethernet aimed at directly handling the network speed bottleneck, because the Ethernet was already there, and they tried to depend on some complementary technologies to alleviate the protocol processing and IO bus bottlenecks. We'll see how actually they did that. Okay. Any questions so far? We're at like 100,000 feet level. I mean, over the next few hours, we'll go back to the 5,000 feet levels. Any questions, comment, please post it on the chat. Is everybody awake? You see, this is like the very difficult in the Zoom.
Yeah,
I hope
please
all of
post
you
your
have
question.
good amount of coffee. Why ATM died? So that is a good question. So the ATM was actually, because they took this telephony world, the fundamental things was that every packet, they had only very small 64 bytes kind of things. Okay. So that was good for telephony, because in the telephone, like when we are talking, you convert into real line rate, and then the digital one, with very small packets, you can send the things. But the computing environment, like you cannot just deal with only 64 bytes. I have to send like a storage file system like a 2 gigabytes, and see how many packets you need to send. And every packet processing had overhead. So then you are not getting very good performance in this kind of environment. So that was one of the foundational things. And of course, there were a lot of other features they introduced, but it was not able to get the traction. Any other questions?
Yeah, I don't see anything. Yeah, now there is a question.
ATM was a committee decision. Yes. It was like there was an ATM standardization committee, ATM forum, just like the industry consortium. That there was a consortium like that, and they were trying to define the features. Okay. Anything else?
I don't see anything on the Slack.
Okay.
Also.
Okay.
Yeah.
Okay. Thanks. So now let's move to the next one. So before we go into, let's take a little bit of look at some of these things just to have an overview. So I'll start with Infiniband. So because this is a lot of initiative happened during that time. So in the beginning, this Infiniband Trade Association was formed with 7 industry leaders. I mean, some of them even don't exist today. They have been acquired by others. But the goal, if you see, if you just read it, it says to design a scalable and high performance communication and IO architecture by taking an integrated view of computing, networking, and storage technologies. So people earlier used to think that, oh, I'm just networking guy. Okay. Just think of like, let's say car. If you just think like a very narrow manner saying, oh, I'm designing the tires, yes, you will design the tires, but tires also interact with the entire engines, the speed, and all those things. So you need to take that bigger picture in mind, and that's what this they started doing. Say they wanted to take an integrated view of computing, networking, and storage technologies. And after that, many other industry participated in this effort. Okay, so in fact, if you go back almost like 22 years, we are coming very close to that. On October 24, 2000, the Infiniband architecture was introduced. It was like a volume 1, version 1, they said. Then over the years, of course, a lot of clusters have been deployed over the years, and each time the system sizes grew, people found out more and more issues. Okay, so then what happened? A lot of annexes were released. I mean, again, Infiniband is a trade organization. If you go here, this is how the main webpage, infinibandtradeassociation.org. So then over the years, a lot of these like a excuse me, like erratas or annexes, they call it, like a newer and newer features have been introduced, like RDMA-CM, ISOR, XRC, Rocky V2, virtualization, etc. So there is the latest version is 1.4. Okay, if you go there and then sign up, you should be able to download the spec. Okay, but but if you download, you will see the latest spec is 1700 pages of document. Okay, 1700. So it is not just like a 2-page brochure. Okay, and that's what the it's like an open standard, and the each and every pieces are discussed. And of course, in our tutorial, we'll spend might be 30 minutes or 25 minutes to give you an overview. So in by no means you will be an expert of any of these networking technologies, including in Infiniband. So of course, you will get a high level picture that will allow you to understand how the systems work. But if you really want to be a designer, like if you want to design a network A or network B or network C, you have to really understand all those specs and then trying to make those design decisions yourself. So similar to Infiniband, as I said, Ethernet was there. So they wanted to define high-speed Ethernet. So as in earlier slide I indicated, 1 gigi was there. So they wanted to design this 10 gigi that time. Sorry, 10 gigi was there to achieve. The objective was very similar, to achieve a scalable and high-performance communication architecture while maintaining backward compatibility with Ethernet. Okay, because that was important, because Infiniband is totally new, so they were able to define a lot of new features. But since Ethernet was there, you have to provide the backward compatibility. So it was good for 10 gigi. But then what happened over the last 20 years? A lot of things have happened here. So let me give a very quick overview here. So typically in the Ethernet world, if you see like a 10 megabits, 100 megabits, 1 gigabit, 10 gigabit, the next was very natural, 100 gigabits. Okay, but then what happened when people wanted to go from 10 to 100? There was a big jump. The consortium was ready to move ahead from the networking part, but if you remember, the IO interface was not ready. Okay, so if the IO interface now is not ready, even if you try to bring 100 gigi, nobody is going to use. Okay, but by that time, actually, Infiniband was moving. In the next slide, we'll show Infiniband went into like a SDR, DDR will introduce all those speeds. So they had come to 40 gigi, okay, 40 gigabits per second. So that's why instead of jumping to from 10 to 100, so they introduced a middle one called 40 gigabits. So this is what like a 40 gigabits for server and 100 gigabits for backbone Ethernet was introduced. There was a lot of debate. There was a voting took place in the Ethernet consortium. So this was like there was a working group. So this is defined as the 802.3. So then as it evolved, gradually we'll see again the PCI, PCIX, how things have evolved now with respect to even the cables, how you design these cables. These two fields like are trying to merge a little bit, both InfiniBand and high-speed Ethernet are trying to effectively utilize similar cables. Okay, so that has led to this kind of a 25 gigi, 50 gigi in intermediate ones. So there is a 25 gigabit Ethernet consortium was introduced in 2014. So now you actually see Ethernet in all different speeds and very similar to InfiniBand, we'll see. Okay, because many of these are actually using the same servers, the same IO interface bottleneck. I can just only change the network adapter, whether I use a Ethernet versus InfiniBand or some other network. And of course, Ethernet has also been giving a lot of focus on the power consciousness. As you are designing very large scale system, power is becoming very important. And then people are trying to make make sure that let's say you are not communicating, two servers are not communicating. Should I keep the link alive, or can I pull down the power so that it goes into some low state? Just like the processor, similar things we can do it to the link. So of course, this field Ethernet Alliance is going strong. Here is a pointer. You can take a look and then see how they are trying to look forward to the 2026. So now let's take a look at only these two examples, because these are like a established things. I'll try to explain these bottlenecks, how they have alleviated it. But of course, all other things, if we talk about Slingshot, if we talk about Omni-Path, later on we'll see all of them also try to handle similar things, but in a little bit different manner. Okay, so we'll just take like a case studies kind of things, Infiniband and high-speed Ethernet, to understand how these technologies help to alleviate this network speed bottleneck, protocol processing bottlenecks, and IO interface bottlenecks. So let's start with Infiniband. If some of you are not familiar, Infiniband actually stands for infinite bandwidth. Okay, it is actually two words been put together. That's how the Infiniband comes. So you remember I introduced saying PCI, PCIX, they were bus-based systems, so there were a lot of crosstalks. So that was the fundamental things they wanted to alleviate. So what they tried to do, instead of as a bus, they came up with this bit serial differential signaling. Okay, so what does that mean? So it's actually an independent pair of wires to transmit independent data called a lane. Okay, so that means I'll have a pair of wires, and I'll just send data in a serial manner. I'll not send it in actually in a bus manner. And then at any time, we'll see that I'll still have 2 degrees of freedom. How many lanes I put, and then what should be the speed of my lane. Okay, just like the earlier we had 2 degrees of freedom, like how many bits per bus, and then what is the speed of the each wire. So they got that concept, but instead of a bus, they made it a like a independent pair of wires. So now if I do this, that is where this idea of infinity came. That means as the demand increases, it should be able to actually keep on adding more number of lanes, and then keep on, depending on the basic technologies, the networking and encryption technologies and all those things, how fast we can, oh, sorry, not encryption, encoding, decoding technologies, how fast we can actually derive that. So that's what led to infinite bandwidth. And let me explain that a little bit in a much more concrete manner. So we had seen this network up to 1994. So this InfiniBand, here I'm putting 2001. The standard came in 2000. People started experimenting with 2000. So the initial technology, it had only one lane. It's called 1x. And the technology is called SDR, single data rate. So that means if I have a clock, in one clock, I'm sending only one bit. Okay. And I have only one lane. So with that, the actual bottom line speed was 2.5 gigabits per second. But that is at the physical layer. Okay, and until that time, all networking, even Ethernet, was using 8 to 10 encoding decoding. That means if I have 8 bits, then over the network I send it as a 10 bits. I do some encoding, and then the other end I do the decoding. So here we are trying to put the payload rate just to normalize across different technologies. So from the 2.5, it actually becomes, the payload is 2 gigabits per second. And in the similar time, this 10 gigabit was introduced, and this was actually the payload. So in fact, the physical layer, it was 12.5, okay, with the 8 to 10 encoding. So then you will see in the 2 years what happened. Better servers came, server speed was increased, so they wanted more speed. So what Infiniband Consortium did, they had the same SDR, but instead of one lane, they moved to 4 lanes. Okay, so with that, they were able to increase the bandwidth from 2 to 8. So then in 2005, in another year, they kept the same 4 number of lanes, but the speed they changed from single data rate to double data rate. So what that means is, in one clock, instead of sending 1 bit, I can send 2 bits, one up and one down. Okay, so then my bandwidth also doubles, 16 gigabits. In fact, during that time, IBM was, of course, a member of the Infiniband Consortium. They, in fact, were thinking very big. They had 12x SDR. So they went with a 12 lanes. So in fact, the cables were very thick. I mean, you can think of like each one is a lane, and then you take these are like a twisted pair, and then you put 12 of these together into a single adapter. But then what was happening, the adapter width was so big. Okay, and not only that, the weight of that link was also very heavy. So some systems got deployed, because at that time, to as a competition wise, IBM was able to deliver almost 3 times or 2 times or 1.5 times their competitors. But then they had if you know, so these were technically good, but from an engineering side, it was a nightmare. When people were trying to deploy these, the adapter used to get bent because these cables are so thick. So in a production environment, there were a lot of errors and all those things, even though you have put a lot of money, but the system was not reliable. So that got actually that product was killed. It didn't proceed, but they were way ahead of time during that. So then if you see another 2 years, excuse me, the technology same, the 4 lanes remained, but it went to a quad data rate called QDR. So that means in the same clock cycle, instead of 2 bits, I can send 4 bits. So then that helps me to move to 34 gigabits per second. And then this is where I introduced in the few slides back, the 40 gigabit Ethernet was introduced because the IO interface was handling 40 gigabits per second that time. Because of the QDR technologies, and the servers had come with those kind of IO interface, and then the Ethernet can actually directly work with that. So that's how 40 gigabits was introduced. Then in 2011, another major things happened. It's actually a little bit of deviation. This was going in power of 2, like a 2 bits, 1 bit, 2 bits, 4 bits, but they went to 14 data rate. That's how the FDR was introduced. In one clock cycle, they were able to send 14 data bits. And another innovation happened. Until this time, it used to be 8 to 10 encoding, but the encoding community also came up with better and better schemes. So they moved to 64 to 66. Okay, because if you have 8 to 10, you're almost wasting like having an overhead of 25%. Okay, so even if you go for higher and higher bandwidth, you are wasting 25% in the encoding decoding. So they were able to come up with better 64 to 64 6-bit encoding. And then if you do a maths, that was the first time they had 54.6 gigabits per second in with one port. And that time Mellanox also introduced this dual port, dual FDR, keeping the same 4x. So if you do multiplication, it was like 2012, they were able to claim that, oh, we can actually support 100 gigabits per second. Okay. So then 2014, and gradually, I indicated earlier, this cable industry and all were trying to, instead of remaining separate, they were trying to utilize each other's technologies. And this is where, like, gigabit Ethernet was also introduced, like at 25 and 50. If you just use only one lane, you go with a 25. If you use 2 lanes, you can do 50. And then 100 gigabit Ethernet was introduced in 2015. So these were between Infiniband and Ethernet. And then, of course, Omni-Path came. We'll talk about that later on. Omni-Path was not a very new technology. It was Infiniband, QLogic Infiniband. Intel acquired and modified the names. We'll talk about that more later on. And they introduced this 100 gigabits per second. Then Infiniband in 2015, it went to, from FDR, it went to another thing called EDR, enhanced data rate, they called it. And that was like 100 gigabits per second in a single port. Earlier it was dual port. In a single port, they were able to deliver 100. Then they have the HDR called high data rate. They are like, the consortium is running out of alphabets, how to define them, but still, English alphabet, we have A to G, 26 options are there. Okay. So in the 2017, it was 200, then the slingshot 10, 11 came. 10 was rocky. Now there is a lot of focus on slingshot 11. We'll talk about that later, which 200 gigabits per second. Then there is a company called Cornelis Network. We'll talk about that. They have taken the Omni-Path and they have modified it to called Omni-Path Express. That supports 100 gigabits per second. Then Google introduced this last year, their Aquila network, that is 100 gigabits per second. And Infiniband, just last SC, they mentioned about this, and now you will see some like versions are coming out. It's called the NDR. Okay, next data rate they call it. Again, in fact, in Infiniband consortiums now has stopped defining all these names. So that is for 400 gigabits per second. So if you take a look at now over the years, just take a look at like a 2001 to 2021 or 2022. Just in the last 20 years, this bandwidth has increased 200 times. Okay, so that's what is actually having a very big impact on how these modern systems are being designed. Okay, whether it is an HPC system or a big data system or AI system, cloud, file system, because you have this bandwidth is increasing, and that was the whole idea of this Infiniband, infinite bandwidth, and that means you need to rechange your designs from the upper layers to take advantage of this. Okay, and that's what exactly is happening here in the community, and we are a part of that, and that's how even you see in the Hot Interconnect main conference, you see all these innovations being presented at that every year. Any questions on this? How the network speed bottleneck is being resolved with the high performance networking? Um, okay, there are two questions. Where and how are these high-speed networks are used inside data center? That is a good question. So it actually, there are, of course, different data centers use different things because of their need. If you just go to Google, of course, sometimes they focus on their Ethernet. They have their own Aquila network. If you go to, let's say, many years back, Bing, which is a search engine in their data center, they were using InfiniBand. Facebook, to the best of my knowledge, now uses InfiniBand, or they sometimes even they mix and match depending on the data centers. If they are doing some deep learning aspects on some part of their data center, they are using InfiniBand, might be they're using Ethernet. um, so it is a mix and match you need to see. Just like I gave the example of like purchasing a car, you need to see what is good for you. Okay, if you are a family of 4, you want to try to purchase a van, or if you are a family of 2, you might want to go to a smaller car, and depending on your budget. So this is the whole commodity networking market, and different vendors are trying to come up with different variations of those products to match with the need of the data centers. So the next question is it possible to increase the network speed at this rate in the future? My answer will be yes, but of course there is a technological aspect, then there is a marketing aspect. Marketing, when I say there has to be a need, like a demand and supply, and people should be willing to pay also. So it is not very easy when you change from 200 to 400 gigabits, right? It needs a huge R&D investment. Are there enough demand for people to pay more money and then try to purchase that? So at least in the last 20 years, based on the data I have shown, I mean, it is improving. So my best hope is that it will keep on improving even for the next 20 years. Any other questions? Yes. So there's a things from Pete. Is it worth mentioning for the audience that for HSC and other protocols, 100 gigabits per second would actually be 4 by 25? Yes. So that's why I introduced. So depending on like how much speed you have, like you can use only even a 25 or even a 2 of 50, or sometimes in this you have a one port, but then it might be going into 4 different parts, which is 25 gigahertz per second. Okay, and that will also gradually will introduce the topology and all a little bit later. So there you will see sometimes if you have a torus topology, you may need to think a little bit differently. Every port has some bandwidth, and then you can aggregate those bandwidth so that I can actually spend data in different dimensions. Okay, so good that you are asking questions. So please continue to do so, so that all of us are will remain awake. Okay. So if there are no question, let me go to the second bottleneck, protocol processing bottleneck. Okay. So the protocol processing bottleneck, let me close this chat here. Okay. So this field, I mean, this idea came almost again in the very late 1990s. Okay. So the idea was that think of like in our day-to-day world, in any organization, I'm sure some of you are managers or big executives, some of you are students or somewhere in the intermediate levels in your organization, but there is always a concept of executive and assistant. Okay, so that means there are some executives and there could be some assistants helping them. Assistants or secretary, I will use the general terminologies of assistant. So then the question is, think of like in our modern computing environments, think of like a processors are executives, and the network adapter is like an assistant. So just like what we do in the real world, can the executive offload certain things to the assistant? If I can offload, let's say I need to send some 100 emails. I can upload to somebody, then I have some more cycles to spend on the decision making. Similarly, if there is a video conference call needs to be set up, I can do it. But if I have an assistant and the assistant can actually do it, then I am free. And once that task is done, I can actually coordinate. So that was the idea. People started working on saying, how do you design these intelligent network interface cards or intelligent assistants? So in fact, can I offload some part of the protocol processing or even support entire protocol processing? Okay, so this is known as like a hardware protocol offload engines. But then there is a hardware aspect, then there's a software aspect. So just like in a normal world, if an assistant has been with an executive for 20 years, he or she knows what to be done. The executive just say, oh, this meeting with this company, assistant knows what to do. Okay, so that is that communication. It's a rich communication interface. It has to be established. Then this kind of um, offloading can happen very nicely. And over the literature, like people have introduced this a lot of concept like a user level communication, OS bypass communication. There are a lot of terminologies are there. We'll take a look at some of those things. But for the time being, let's think of like a user level communication, and that actually gets rid of this intermediate data buffering we saw with the traditional TCP/IP stack, and and then there will be no software signaling between the different communication layers. All layers can be implemented in a dedicated hardware unit, and then things will improve. And that's what all modern networks do. Okay, so that's why when we say that, okay, the very latest you will see, oh, this technology is trying to deliver 1 microsecond latency between a sender and a receiver in two different nodes. It's possible because of all these kind of things. Okay, but here another thing we need to keep in mind, and that will come gradually later in the presentation, what is the cost? Okay, so I give this typical example. Think of like an executive having a secretary or an assistant. If the assistant has a PhD degree, imagine, okay, what can be offloaded? Everything. All right, you tell your assistant saying write a proposal, get the funding, write the paper, write the report, just put my name there, right? But to have that kind of a assistant, you have to pay quite a lot. On the other end, if there is another assistant which has a reasonable like a BS degree or something, they might have some capabilities. So that is the level of capability you have to offload. So this is where the cost performance trade-off comes in. Okay, of course, a vendor can go and then offload more and more things into the adapter, but then how that cost will go up, and is the community ready to purchase those adapter with that higher cost? And that's what we'll see a little bit later. Then the third one is IO interface bottleneck. So this is very interesting. So if you remember, I indicated like this PCI, PCIX, then they went into bit serial differential signaling. But then when Infiniband was introduced, many times if you see the server architecture, I need to send data from memory of one node to the memory of other node. Okay. But of course, the network adapter is connected to the IO interface. So if I want to get the full speed, I need to actually extend my network adapter logic to even to the memory, so that I get the data from the memory of server or sender to the memory of the receiver. So that was the whole idea of Infiniband when it started with. And once Infiniband started picking up in the early 2000, what happened? Intel was a part of it, and of course, Intel is a part of PCI consortium also. So there is a big friction started. Okay, and I'm just telling you from all technical angles. Many of you might be working at Intel and all. No offense to anybody. I'm just as an outside observer, I'm telling what happened. So then Intel was looking at saying the Intel had to expose its internal design for the Infiniband to actually come to the memory, and they were not ready to do that. Okay, so then at some time Intel actually introduced saying that, you know, in the Bay Area, I mean, many of you are in the Bay Area, there is always every company, the bottom line is money, how much money you make and how you kill your competitors. Okay, so in the beginning, some consortium opportunities come, 10 organizations jump in. Of course, you are collaborating, but the end goal is that I should be making more money than somebody else. And if that there is time comes where you are losing and others are winning, a typical thing is that you withdraw. And then if you have power, you can kill that. Okay, so that's what Intel tried to do in the mid 2000, saying that they are no longer a part of Infiniband consortium. And of course, Intel works very closely with Microsoft. Microsoft also say we are not a part of this. So like this, a lot of this turmoil happened. Okay. But then what was happening, it was not a war in the networking field. At that time, there was another interesting thing was happening is the GPU technology was evolving. Those are the mid 2000. If you go back, even Nvidia was not even a big company like that. People were using the GPU adapter, like a CUDA came in saying, okay, the GPU adapter can actually be used now for computation. But then the critical factor was that how do I send data to the GPU? Okay, so same whatever the Infiniband was trying to see, how do I move data from memory to adapter at the sender side and adapter to the memory on the receiver side. The GPU community was facing the same problem. The data transfer was taking a lot of time. So then Intel was getting banged from both sides, from the networking field as well as from the storage field. And then, of course, again, this is a third rule of any company. If you cannot win, you join with your competitors, am I right? And that's what happened. So Intel then started thinking, saying, why we are sticking to only PCI? Why don't we adapt these lane concepts which Infiniband is introducing? And this actually led to this PCI Express. Okay, I'll show that in a little bit more in the next slide. And then once that came, everybody was happily married together. Okay, so that helped to solve the networking problem. It was trying to solve the GPU problem, and then Intel didn't have to expose their internal design. So these days, Infiniband, high-speed Ethernet, or Slingshot, or Aquila, you name any of these adapters, it actually comes as a network adapter that plugs into existing IO technology. And that existing IO technology is mostly the PCI Express. So if you take a look at this slide, they adopted the very idea of all those lanes, okay, saying that you have some number of lanes. So whatever was in the network, they extended it over the PCI. So if say you can have X1, X2, 4 lanes, 8 lanes, 16 lanes, and then you can define how each lane is operating. Okay, and based on that, you will see you will have a matrix here. So for a given set of deployment, you need to see where you want to go. Of course, the most common ones these days is this PCI Express 3 is most common. On the AMD systems and all, they have gone into the PCI Express Gen 4. And this is where you will see like you can go up to like a one port, you can get maximum like a 64 gigabits per second with 16 lanes. But then if you want to go into in a single port with X16, you may need to go into PCI Express 5. So like this, they're defining this PCI. As of now, like the PCI 7 also has been introduced. So that's what is shown in the left-hand side. Okay. And also I want to indicate another thing which happens, which is the intra-node networking. Okay. So this is where like Intel has been using QPI. So that means from socket to socket communication. AMD has using hypertransport. So those also coexist. What comes outside is like a PCI Express. Okay. So effectively you can think of like a sending data from one server to another server. It goes through multiple networks. Okay. I mean, I believe Dan's talk yesterday also highlighted some of these things. You go across a lot of different networks to really get the good performance. And of course, that IO interface architecture is now becoming also a contention point for last several years. Even though PCI Express was there, because PCI Express is still being controlled by Intel and all, many years back, it didn't move faster. And that actually forced NVIDIA to introduce their own link called the NVIL link. And that's how, if you remember, like a few years back when Summit was introduced, it was a consortium of Mellanox, NVIDIA, and IBM. So they were bypassing the PCI Express for connection of the GPUs because they wanted to connect more number of GPUs into a single server. So they introduced their own NVIL link. And we'll be talking about that a little bit later. But now, actually, there's a lot of actions are taking place. The CCIX is gaining a lot of momentum. There is a Genji, there is a CAPI. Many of these are a little bit different in the sense, instead of message passing, they actually use load store. Okay, NVLink actually does load store. I can actually use load store concept across devices. And they're now trying to take it, these other architectures, and then trying to see from a given server to the other server, can I actually do in load store, because those are faster than sending us messages. So we'll see a lot of actions along this direction in the next few years. Any additional questions, comments here? Okay, if not, let's move. So CCIX, OpenCAPI, GenG have been absorbed by CXL. Yeah, thanks for that comment. Okay, so that's they were actually different initiatives, but now they're coming under the same umbrella, and that is getting a lot of momentum in the recent years. So before then we go and start talking about the different networks and then see what are their features, let's understand the communication model, because that has a lot of impact. Okay, what do I mean by communication model? So think of, like, I'm trying to design a system. Of course, there has to be some software entity. You can think of an MPI or file system or cloud. Somebody is sending messages, somebody is receiving messages. So what is the abstraction there? Okay, so we'll start with the common one is called two-sided communication model. Okay, and so the two-sided, so before I give it, just think of like emails. I send an email to you. It's actually a two-sided communication model. That means I send an email, my mailer sends mail to you, but unless you open up your mailbox, you don't see. I might have sent it 10 days back, but if you are not opening up your mailbox, you don't come to see it. And after you see the email from me, the control lies with you. Where to place that? Do you keep it, or do you junk it? Do you forward it? So that depends on you. That means for an end-to-end communication, both parties are working together. That's what it says, two-sided communication model. And in the next few slides, we'll introduce the newer model called the one-sided model. So here, if you see, we have said like a very like an animation, we have 3 processes, and SCA is like a network adapter. So in the two-sided model, most of these high performance networks, because of that voice bypass communication and all, always receiver side, we ask them to post some buffer. Okay, that means as if you are ready to receive something. Okay, and then the sender side, like here, let's say I'm waiting to receive from P1 and P3. It's just like a mailbox. That means my mailbox should have enough memory. So if a mail comes, I hold it. Many years back, if you remember, many times if you send a large data, you just get used to a message saying, oh, the receiver doesn't have mailbox capacity. Okay, but these days, of course, memories have become cheaper, and sometimes they do also sender side. If you have a very large message, like let's say 25 meg and higher, it will say no, I cannot send it. Okay, so this is the kind of idea. So the receiver is ready, and especially for good performance, you need to continuously poll. Okay, we'll go into that polling mode, because so that you don't go through the interrupt overhead. So you can think of like these receivers have been posted, and you are polling to get the data. So now when the P3 comes, like it is doing some computation and is trying to send the data, it posts the send buffer, and then as the adapter sends, it comes to the receiver, and since this receiver is polling, it will quickly detect this and then receive the data from P3. Okay, and then same thing happens if P1 sends, you will get it, and then you will get the data. So now you can see, for these communications to take place, both parties are participating, P3, P2, P1, P2. So we'll call this as a two-sided. The other thing is the one-sided. Okay, so let me give a good example. So the one-sided is like a little bit of trusted. I mean, in general, I'll use the word trust. We'll see what happens inside, or I'll say secured kind of things. So let's say I'm in my office here, and I have a very trusted colleague. I have a lot of books in my office. If a friend wants to borrow the book, there are 2 ways. Every time the person can come and interrupt me and say, oh, I'm taking this book, and then in the return, he or she can again interrupt me. But the other end, I can tell this my friend saying, look, I trust you. Even if I'm working, if you want to take a book from my bookcase, my door is open, just come and grab it and take it. And whenever you are done with the reading, put it back. You see? So this is kind of a one-sided, and we'll see how that works. So that means there is some kind of a trust or understanding between the sender and the receiver. So in this case, we'll see typically for any software. Okay, I mean, it could be MPI or it could be some Globus or you name anything, TensorFlow or PyTorch. When you try to do every software has some initialization phase. So in this kind of initialization phase, you can create these buffers, you can do some exchange. We'll see how that gets done. So typically some buffers are posted at P1, P2, and P3. And not only these buffers are posted, their pointers are exchanged. Okay, so just like my friend, I can tell him that, yeah, if you are looking for an architecture book, it is in my bookcase one. Okay, so that the person knows from where to take it and where to put it back. So in this case, what happens? See this animation. After these exchanges are happen, I'll repeat it. If P2 wants to send something to P3, it exactly knows where to put it in the P3's memory. Okay, in the two-sided model, you don't know that. So here, if you see, I write to my adapter directly writes to this, and as soon as it comes, it doesn't have to wait there. It directly goes and writes the data to the P3's memory because I have that information. And this is what later on we'll try to link with the RDMA principle, remote DMA, which is a common word. We'll go into more details. So this is like an RDMA write or a put operation. You can think of, you can also do it in the reverse. And what is the benefit here? The biggest benefit, as you can see, when I'm trying to do this network processing or trying to send the data, I am not taking any cycles out of the buy from the receiver. So that means the receiver can continue to do computation and data can come to my memory, either as a put or somebody can get data from my memory. Of course, synchronization semantics we need to worry about. We'll talk about that later. But then I can exploit a lot of overlap in computation and communication. So that is the key thing with this one-sided model focuses. So there is another example here. Again, you can see directly you write from P1 to P2. But to achieve all these things, this is a communication model. Okay. But now let's bring it back to that user level communication concepts I indicated earlier. Okay. So to achieve these, we need some underlying mechanisms. And this is one of the mechanisms called memory registration. Okay. In most of the computing system, as you know, when we write the program, we write in virtual memory. Okay. But if you are some of you are hardware engineers, you know, like the DMAs and all those things, they don't work on virtual memory, they work on physical memory. So now the question is, who will do the translation? If somebody is sending a message to me using a virtual address, and the receiver side, I need to do address translation and all those things, it will take a lot of time. So then to avoid that, the concept here is that before we do any communication, all memory be used for communication must be registered. Okay, so there is a procedure here, and this is what, when you try to do the registration, typically what happens from a process, you send the virtual address and length to the kernel. Okay, because you want kernel to be involved. It's not a user process, because I don't want to tap like my memory should not be used by some other process, or some other process cannot access to my memory. So I take help from the kernel. And then what happens, the kernel actually handles that virtual to physical mapping. It takes some time, of course, and pins the region into the physical memory. Okay, process, typically you cannot map memory that is doesn't you don't own. But then these adapters, what they do, this is the third step, which is mostly important. The adapter or the SCA, or you can say RNIC, I mean, there are many terminologies there. It actually caches the virtual to physical mapping and issues a handle. Okay, so not only you do the address translation, you also cache that information in the adapter, and you give two keys. One is called local key and another is called a remote key. Okay, and what is the ideas of those keys? And those handles are returned to the application. And then what happens, the next time I try to do the communication, I don't have to go through registration. I can only operate on those keys. So that means you see this diagram. If I want to communicate, I directly use that L key or a local key to tell the NIC saying that I want to send some data. And then if you see it very clearly here, I am not going through the kernel. And that is the key thing. And this is what is known as OS bypass or operating system bypass, kernel bypass. So these are the modern protocols. So that means when I'm sending data, my sender path or receiver path, I'm not touching the kernel. Because once I go through the kernel, it has overhead and it will keep on adding time. So first I register and then I use them. So that is the whole idea of the L key. Similarly, you can do remote key. Okay, like you remember the one-sided model I introduced. So I can generate a key and I can give it to my friend, and then or the receiver, the other remote, when it sends me a message, not only it sends the data, it also sends me that R key, and both things needs to match. Okay, so this concept was very clear in the beginning of the InfiniBand, RDMA, all those things started. I just want to indicate that when they started this R key, it was not encrypted. Okay, so the idea was that you are communicating within a node, within a room, unless you physically go and tap some machine, you don't try to extract. But later on, of course, InfiniBand or modern networks have actually gone wide area. So there actually they do the encryption. Okay, so there are technologies out there, they do the encryption. But here the main idea is that I can send the data both at the sender side and receiver side with very low overhead. Okay. So now let's put all these concepts together, and there are some very nice animations here, and then we'll go this to get a complete understanding, and then we'll go into the, might we take a break and then come back and then talk more about the others. So so we talked about this two-sided model. So here it shows animation, and we'll use some terminologies here like a InfiniBand terminology, but again every network adapter, they're equivalent things. Okay, so we'll introduce that a little bit in a formal manner later on, but something like a queue pair, like I have to establish a queue pair, like a connection to communicate. So here what it's trying to show, I have processors. These are like a memory. I have a queue pair. There is an InfiniBand device. This is that intelligent assistant kind of things. And there is something called a queue called CQ. Let's not worry about that. This is the sender. This is the receiver. So, so based on that earlier example, if you see, if I'm trying to receive some message, I said like you have to reserve some buffer. And that's what happens. Or here in the InfiniBand terminology, it calls something called a wookie, like a work queue element. Don't worry about a lot of these terminologies. Okay, it is like a task or some descriptor. Think of like the processor, the receiver is telling the network adapter saying, yeah, I'm waiting for a message from this sender. Okay, so you post this, then what happens, the important thing, let me go back. So this receiver wookie has knowledge that if a message comes, what to do with it. Okay, that is the information there is in the wookie saying, okay, if it comes from process 10, I need to put it in this memory. If it comes from process 20, I need to put it into this memory. Okay, so then on the sender side, whenever the processor has finished the computation, it has to communicate, it also initiates a similar descriptor or wookie, and that can have information on where the data exists in the memory. It is just like, the executive talking to the assistant. You tell that, okay, this piece of text has to be mailed to 10 people. Okay, so that is kind of a descriptor. You give that information to your assistant. In this case, the processor will give that to the adapter. Then it is left to the adapter or the assistant. It will actually see the animation. It'll grab that from the task queue. It'll actually go using a lot of DMA engines and all. You will get the data from different memory. It could be contiguous, non-contiguous. There are different semantics. It will get the data, put them into packets and all, and it'll try to send it. Now the question is, it reaches the receiver, and this is the two-sided model. You remember, this is like a send receive model. So this message doesn't know where it will be put. That control lies with the receiver. So this is where what happens, there is some kind of a matching takes place. Okay, there's a message has come, there is a descriptor, and after the match, the data actually goes and gets written to the memory segment. Okay, it is the same example of that email I indicated. I send an email, you invoke your mailer, you find out my email, read it, or do whatever you want to do, delete it or store it or put it into archive, tag it. So that's the kind of things what we are trying to do. And once that happens, you actually, there is something kind of a completion queue. This is just like an executive and assistant. The assistant has finished a task. He or she has to inform the executive saying, I'm done. All right, typically through again an email or a phone call. So same idea here. Once the task gets done, you have something called a completion queue, and then you put an entry there. And then the executive can come, either do the polling or it can generate interrupts. All those options exist. And then you basically send an ACK back to the sender, and then the sender also, sender side puts an entry into its completion queue saying it has finished. So that is kind of a two-sided model. So now if you see, we talked about all these overhead and all. If you take a look at this in the actual data transmission or the network protocol processing perspective, What did the processors do? Processor did very little. All right, because these network adapters are intelligent, I just gave a descriptor on the sender side and descriptor in the receiver side, and I may need to spend few cycles to go actually to grab something from the completion queue, either on the sender side or receiver side, to see whether the transfer has happened or not. Okay, and that leads to that CPU utilization. You remember I introduced that CPU utilization. So if you follow this kind of model, your CPU utilization is very low. Okay, so processor is involved only to post send key, posting send key, receive key, and then pulling the completion cookies. All other cycles are left for your computation. Okay, but then let's see the, yeah, go ahead.
Dr. Panda, there is a question in the chat.
Yeah.
In the one-sided communication protocol, how could the sender be sure that the receiver buffer or memory is full or is capable to receive?
Yes. So I'm talking a little bit at a higher level. Below that, you can see some credit-based mechanisms are there. Okay. So typically this below, you can say, okay, I have so many buffers of so many message sizes. So it gets translated into some credits. So as the messages are coming, and if the, like, the sender sometimes knows that there are so many credits, there also is a protocol saying if it goes above, the message actually gets dropped. Okay, so the sender will know, like a RNR kind of signal it will get. So that means the receiver is not ready. Then some below, there's some more credits have to be done, more buffers have to be posted. Okay, so I'm just explaining this at a little bit. Let's say might be at 20,000 feet at this time. We're not going into very like 5,000 feet, because it will take quite a lot of time to go over all these differences.
So there are two other questions. I don't know.
Yes.
It's up to you whenever you want to take.
Yeah. No, I can take that. Are these proprietary network proposals still active? Will industry consolidate more some of these proprietary protocols? What is the difference of NVIDIA VLink versus UCF presented yesterday? Yeah, so there are a lot of things here. So what I'm actually trying to show here is actually Infiniband. There's a concrete example in Infiniband, Rocky, even some part of Omni-Path. These have been there for 20 years. So these are not proposals. These are already running on many systems. The wait for the difference between NVIDIA, the NVLink, we have actually a section dedicated for that. UCF is a little bit different. That is a software architecture. We'll talk about the UCX. So UCX is a part of the UCF foundation. So that is a software. So by the end of this tutorial, you will get answers to all those things. Okay. Is SSH an one-sided model, since we can move local files to remote servers directly with SSH? Yes, it's like the SSH, RPC, all those things are similar kind of ideas which are there in the distributed computing environments, but these are heavy weighted. Okay, so it takes a lot of time. If you try to measure like a SSH, it is in seconds and all. Here we are talking in microseconds. Okay, so that's how we are introducing all these mechanisms, so that I can actually try to take care of this data transfer at that microsecond level. Okay. So let's move ahead. So we saw that. So now let's see the same animation. Now let's try to see with the RDMA model. Okay, that is the one-sided model, you remember, and I am assuming many of you know RDMA. If not, I can very simply explain. DMA is the direct memory access. Everybody knows that, right? It has been there in the computing field for many years. Even within a single server, if I want to send data from, let's say, memory to IO or IO to memory, processor can always do it. You write a program using load store. I'm loading from your storing. But then if I do that, I am totally busy in doing my IO. I don't have enough cycles left to do computation. So this is where the DMA was introduced. That means it is a device. Is think of like a very precursor to intelligent adapter. I give a start address, I give a end address. It is sitting on the same memory bus, and then I give these commands, I program it, and then say go. And once it goes, it does cycle stealing, and then it keeps on moving the data between memory and IO memory behind the scene. Processor is totally left. It can do computation and comes back, check on a tag, or saying that, yeah, when the completion has been done. Okay, that was there within the node. RDMA took that concept that R stands for remote. So the idea was that can we use the same concept and take the data from memory of a sender to a memory of a receiver across a network. That's why the R comes. And I can do very similar to like a DMA. I can do a write, which is a put operation, or I can do a read. I go and then read, which is a read operation, RDMA read operation. So that matches with our communication semantics. If you remember, communication model is the higher level and the RDMA is a lower level. So you can actually, there is a lot of combinations. You can actually implement even a one-sided model on top of two-sided mechanisms, or one-sided with a one-sided mechanisms. So those are a lot of different implementation issues. But now if you see in the one-sided model or in this RDMA mechanism, and by the way, RDMA, Infiniband, prior to Infiniband, people were talking Quadrix. If some of you remember, like there was a networking technology called Quadrix, it had actually introduced some of these things, but Infiniband brought it in a big manner, RDMA. And that RDMA has been adopted by all other modern networks. Any networks you talk at the lowest layer, that RDMA mechanism is there. And all the software stacks have been RDMA enabled or RDMA aware kind of things, because that provides, as you can see, a lot of benefits of this. Not only you can reduce the latency, increase the bandwidth, reduce the CPU utilization, but it gives you that overlap potential of communication with computation, and that boosts the performance of any parallel application, parallel or distributed applications. Okay. So here what happens, the difference, as I showed in the one-sided communication model, the receiver doesn't have to post that initial descriptor because you have done some kind of an exchange of those L keys and R keys. So here what happens, the processor offloads that to the secondaries or the assistant with a descriptor. But now you can see the descriptor has not only information about the send buffer, it has information about the receive buffer. Okay. This is just like telling my friend saying, okay, if you will look architecture networking book, it is in my bookcase number 2 on the third shelf. I give that information. And then if my friend walks into my office, he or she doesn't have to disturb me. I can continue to do my work. And then it can come. So now if you see the animation, you just offload that. And then the adapter actually performs all these things, but now you see this arrow is different. Let me repeat it. Not only it gets from the sender, look at the receiver side. It doesn't wait at the adapter because it has that information where to put it into the memory. It goes and directly puts it into the memory. This is like an RDMA write or a RDMA put. You can do the reverse, which is like an RDMA read. Okay, and then of course the remaining steps, you send an ACK. The sender gets an acknowledgement saying message has been received. Now there is a little bit of trickiness here. There are again some different mechanisms. How does the receiver knows that the data has come? So different vendors have implemented very differently. Especially Infiniband has a very strong order semantics. Um, if the last byte has arrived, it guarantees that all other previous bytes have arrived. Okay, so that actually helps. You can actually poll on the last byte, or there is a way after RDMA write, you do another send receive so that the receiver gets, or there is an option called RDMA write with interrupt. You send another small message. There are a lot of different mechanisms are there which will allow you for the receiver to know whether the data has come or not. So here, if you see, in fact, this model is better than the two-sided. So here you will see the initiator processor is only involved in posting the send cookie, pulling out the completion cookie. There is no involvement from the target processor, nothing. Okay, so that allows you to, in fact, have that overlap of computation and communication going to very high. You can even go to 90%, 95% kind of things. Okay, and if you can design your communication or any middleware perfectly, you will get a very big boost in the performance. And that's what I mean. In fact, we have been working in the MPI, the MPI's library for last 22 years. We exploit this mechanism in a significant manner. All other libraries, MPI libraries, the Globus, you talk about Lustre, these days TensorFlow, everybody is exploiting these RDMA mechanisms because it has a powerful potential to overlap computation with communication, and not only it boosts the performance, it also helps with the scalability also. And I give this nice example. You can actually correlate. I know we are going into in some parts of the place you have either a lunch time or break time. Think of like a very common example. Might be, I'm sure if you're a student, you would have written a papers, or if you're an executive, many times you would have written proposals. And these days we go through a lot of deadlines. All right. I'm working on by night. These days, there's a lot of papers get submitted in AOE in the very early day morning, late night. I'm working. I feel hungry. Then the question is, what do I do? I am feeling hungry. I have deadlines. I have only few hours. So think of like your RDMA model. You have a trusted friend or your spouse or your wife or husband. You can tell them, look, I am working. Please bring the food to my table or to my desk. Okay. So that is like a RDM enabled food is being delivered to your desk. So in that case, I can actually continue to work and eat. I don't have to context switch and I don't have to go and then grab my food. So that gives me complete overlap of computation with communication or my execution with the food delivery. Okay. um, and that's how I can actually, most of the people, if you have that kind of a luxury, you have some friend or somebody is helping, you will see that when a real deadline comes, you will be able to meet that deadline much more faster. Okay. I'm just giving a real life example to correlate. So that was like a send receive two-sided. The one more thing I'll introduce is called atomics. Okay. Again, this was there in some form earlier. Infiniband tried to take it to the next layer, and a lot of modern networks have the same thing. So many times you would have seen, like especially even in the parallel computing or distributed computing, people talk about semaphores, locks, barrier synchronization, and all those things. Okay. So these are implemented many times with some low-level semantics. If you would have taken some operating system class, you would have said fetch and add, compare and swap. Those kind of mechanisms actually tries to achieve you that atomic property. That means if multiple people are trying to access a memory, we want to make sure that only one such person can access that memory at any time. Okay. Because that is a very fundamental concept. The locks, semaphores, and all on top of that, all the operating system and things work. So Infiniband actually wanted to take that, even bring that RDMA into atomics concept. Okay. So the idea here is that I'll try to show concepts of fetch and add. Um, so I have the same kind of a descriptor. So let's say it's a fetch and add with a 64-bit segment. So that means I have some data. The target has some data at a given address. I have to somehow combine. I have 3, might be that memory has 5, 5 plus 3, 8. After that operation, the destination location has to have 8. I also have to have 8. But while I'm trying to do this operation, nobody else can come in between. That is the whole idea of atomic. Okay. So that was the early phase of Infiniband. So if you see the same thing, message comes to the adapter. Now they try to include, like so far we have seen the adapter has intelligence for data movement, but now you think of adapter having capability, or your secretary having more and more capabilities, or an assistant in this case, to perform computation. Okay. So I can take this data and now we can introduce like a operation there. It could be add, it could be max, mean, sum, all those kind of things. And if I do that, then this we are just showing between a single pair, sender and receiver, but in a very big system, you will see thousands of people might be accessing that memory. So all of those will go through the network and they will be sequentialized. Okay. And they will be guaranteed that it will be taking place in an atomic manner. So that was a unique mechanism which was introduced by Infiniband, and it has also been taken by all high performance networking. And that also led to the initial phase of like putting computation in the adapter. But now later on, we'll see even computation is going into the network. If you would have heard of some of the talks in the Hot Interconnect, in network computing, people are putting computational capability into the switches. If you want to do a global all reduce, which is very important for all HPC, machine learning, deep learning, AI workload, can the switches perform that operation? Can the adapter perform those operations? So that intelligence is becoming more and more sophisticated over the years. Okay. And this is one of the concept, again, we'll try to see in the all the modern networks. So the idea is very simple here. Again, initiator processor is involved only to post the send cookie, pulling out the completion cookie, and there is no involvement from the target processors. So even to perform this atomic operation, you can get actually overlap of computation and communications. Any questions here? Is everything is clear? I think people are silent now. Okay, good.
Yeah,
Okay, there's some
please.
questions here. Let me
Some
try to
questions,
take.
yeah.
How many QPs do the devices need to track? I mean, this is a different adapters have different things. Okay, I just introduced the QPs in a single concept. Sometimes you can have different multiple QPs. In fact, we'll see later on, like some networks use multiple QPs to improve the bandwidth. Like a Rockport network, you can go through 2 QPs, 4 QPs to improve the bandwidth. So it is totally left to the upper level software architectures, and of course, depending on with how many nodes you are communicating, you will have so many QPs. So that also brings to some of these overheads, and then we'll spend some time even on the transport protocols. That is actually the underlying. We'll answer your question in the transport protocols, UD versus RC versus XRC versus direct connect. So all of them have trade-off in terms of performance and scalability. Okay, so just hold on, Pete, for few more sections.
There is
Atomics are for,
from,
yeah, atomics are for point-to-point only. Yes, that's correct. Donglai. Okay, so if there are no questions, what I'm thinking is how about we take a 15 minutes break here? Is that okay with everybody? We come back with at 1 o'clock Eastern, and it will be what 10 o'clock Pacific.
Yeah, I think
okay?
That sounds good. Yeah.
Okay.
Thank you.
Thank you.
Yeah.
Thanks. Bye. So those who joined a little bit late, again, the slides are available here, and then please feel free to take a look, and it has been posted, but just you can take a look here. So Hari, you will be able to start from the other section, or do you want me to cover a little bit more? Or
I can take care of it.
We can't hear you actually. I can't.
I can hear you.
Yeah. Oh, okay.
Yeah.
Now I can hear.
Yeah, sure. Yes, I can do it. Yes.
How about the other? We didn't get time to discuss the up to what portion you will cover, and then I come back. You tell me.
It's like it's up to you, Dr. Panda. Like
I can take that Ethernet part.
Okay. Sure.
I'll go. You cover all those. Yeah, there is an Ethernet part there. I'll take care.
Okay.
And then might be
all of this.
Yeah. Then you cover all those things. Then I'll come to the software stacks and all. Okay. Can we double check what happened to my laptop? I don't know why these things are not.
Sure. Let me stop my share.
Okay.
So let's see.
Yeah.
What's going on?
I mean, this monitor also, I don't know. Sometimes it's not getting detected. We didn't get time to. Let me see. Let me open up. So I have this.
Do you have external monitor?
I disconnected it actually now.
Okay.
But what might be my setup? I don't know. I mean, I can show the setup here if I go to.
Saurav, do you want to pause the recording?
Yes, please do.
Saurav, I don't know whether Saurav is on here. Yeah, I'll check with him offline.
Okay, thank you. So. Oh, I cannot. Can I share the screen on the Zoom? I mean, I have opened the PowerPoint. Let me again go through the. I share the screen. It says entire screen, window, and S tab. So I'm taking
so Dr.
the.
Panda, can you do this first? Can you open up PowerPoint in presenter mode? And
I see.
Okay. Can you do this? Can you connect the second screen first? Okay, can you connect the second screen?
Okay. Yeah, in the current setting, my second screen is exactly a replication.
Okay. So then can you make it like go to properties, right click display properties, and can you do extend screen?
But when I say display, it just shows 1 bar 2. And
yeah, so that's because you have put it a duplicate. So in display, scroll down all the way down to multiple displays.
Multiple displays. Okay. Yeah. So this
So
is
click on
duplicate
that
display.
and say extend desktop to this display.
Extend these displays. Okay.
Yeah.
Okay. Keep these changes. Okay.
Yeah, keep these
changes.
changes.
Okay.
Okay. Now, can you open a PowerPoint?
Okay. I have opened.
Yeah, like you can try to set it in presenter mode or whichever mode.
It is not in the presenter mode, and
That's
let me
okay.
share.
So how about this?
Yeah.
Drag the PowerPoint to the second screen.
Oh, it's to the second screen. Okay.
Yeah.
Okay, I got it to the second, like my extended monitor.
Right. So can you click on present from there, or like can you click on present from there?
Okay.
So
yeah. It came. The main screen is coming on the bigger one.
Okay.
And here on my laptop, I see the current and the next one.
Okay, that's a presenter view. Okay, now click on Zoom and can you share your second screen?
Okay. I'll what do you see now?
I see your first screen, Dr. Panda. I don't see the presentation. Okay, like click on Zoom and share the other screen, not this one.
I mean, took to the second. Somehow my screen is. Here I see left side, but it's actually the cursor is going to the right side.
Oh, okay,
that
so then you will have to invert it. So can you go to display?
Okay.
So now in display, display settings. On the top, there is a thing for rearrange your displays. Do you see that?
Okay, let me go there. Yeah, it says 1, 2.
Yeah, so drag, grab 2.
Oh, okay.
Yeah.
I see.
So
okay.
whichever side you want.
Okay.
So you can rearrange it. Then you click apply. Then you will not have the confusion.
Okay, apply. Okay. Yeah, that is good. Okay, so at least that got done. So I have opened that, let's say in the first screen.
Now forget about everything. Can you just share your big screen, like on Zoom? Just say click on share and share your other screen.
Okay.
Yeah. Okay, now the big screen is completely empty.
Okay. Yeah.
Now you can maybe if you want to, you can drag the PowerPoint there and.
Okay. So I take it there.
Yeah. Now you click on that
presenter mode.
Yeah. Yeah. Now I see the slide in full view. Okay.
Yeah, you see, but on my laptop I see the.
That's okay.
It's
because,
okay.
No. So do you want it so that one screen is usable by you and like for other things other than presentation, and you present from this? What do you want to do?
I typically feel more comfortable the main screen remains on the laptop.
Okay, so then very simple, like move the main screen over here.
Is something in the display setting I do, or
no. Close presentation, stop sharing.
Oh, okay, stop sharing.
And come back here, like drag the presentation back to your laptop screen, please.
Okay. Yeah, I brought drag the things.
Okay, now can you click on present 48? Okay, so in slide number 148, please, there'll be a link. So can you click on this link? That will give you the necessary usernames and passwords to access the remote cluster. Okay, so that will take you to a like a Google Doc. So what I'd request that you do is here in the Google Doc. So this is for so please claim a particular username and password. Okay. So just like it is shown here, like put an X somewhere. So please use this username and this password like listed here, okay, to log on to the cluster. So the cluster is RI2 at the Ohio State University. So please use the username and password that you obtain here to log on. Once you log on, you will go into, like, please go into this particular directory, tutorial IB, if you are not already taken there. Okay. Inside there, you'll see a bunch of scripts. So folks who are interested in doing the hands-on, can you kindly let me know if you are able to log on to the system? Are you guys able to log on to the system? Okay, maybe yes. I assume that you guys are able to log on. And okay, if you guys face any issues, please let me know, and I can help out with that. So now that Saurav is back and he has started the recording, let's go ahead and continue with the presentation. So before the break, Dr. Panda had discussed about like the various communication models and semantics. So now we'll be talking about different interconnect architectures and their particular features. Okay. Again, this is not like an in-person conference. I can't see most of your faces. In order to keep things interesting, let's ask questions. Okay. That will help to keep everybody awake. Okay. So we'll first talk about InfiniBand high-speed Ethernet and their convergence. Okay. So when InfiniBand and Ethernet started out, it was like Greek and Latin. They wouldn't talk to each other. Okay. So that isn't good for anybody. So in general, what people were trying to do over the last several years was trying to see how they can be brought together so that the InfiniBand speaking applications can go over Ethernet hardware, and Ethernet speaking, let's say socket speaking applications can go over InfiniBand hardware. So we'll be talking about all of these things. So broadly, the goal is to present a high-level picture of various protocol stacks and describe how they interact with each other. Okay. So we'll start with InfiniBand. So let's try to see how the InfiniBand and the traditional networking stack compares with each other. Okay. So just like your traditional like OSI stack, you will have the application layer, transport layer, network layer, link layer, and physical layer. Okay. So this is how the standard stack looks like. The main differences are that is one, the interface between the application and the transport layer. So it is sockets for your traditional Ethernet network, but for IV, it was something called Open Fabrics Verbs. In the sockets world, we had TCP/IP and UDP. I assume that everybody knows what TCP/IP and UDP is. So long story short, it's a reliable and unreliable protocol, which is very commonly used for communication on the internet. We have the equivalent of that called RC, which is reliable, and UD, which is unreliable. Then you also have similar concepts of routing and switching and the network layer. You have flow control, error detection. And similarly, you have what is called as a subnet manager. So a subnet in the InfiniBand world is similar to like a local area network in the Ethernet world. And there will be one entity called the subnet manager to manage that. Okay, so at a high level, this is how the stacks compare with each other. Okay. Now, broadly, what we are trying to do over the next several slides is to fill up this particular slide. Okay. We'll try to show you different ways in which the application or middleware can communicate over various high-performance networks. So what we all grew up with the programming was sockets. Okay, sockets will typically go over TCP/IP or UDP, and you would have an Ethernet driver, an Ethernet adapter, and an Ethernet switch. So the first thing that happened was the advent of IP over IB, so that people can use, let's say, sockets-based applications over InfiniBand systems. So this is one level of convergence that was brought out. Okay. So you have this on the one end, and on the other end, you have RDMA. Okay, so where you have the verbs interface, and all the communication takes place at the user space, and minimal handling happens at the kernel space. Okay, and this is one of the major differences between your sockets based communication and your verbs based communication, that most of the critical operations of data transfer happens in the user space without having to go into kernel space and incur an expensive IOCTL card. So that is one of the main reasons why you are able to obtain high, like low latency, high bandwidth communication over RDMA or high performance networks. Okay. Now let's see how InfiniBand has evolved over the last several years. So we started with SDR, which unfortunately we are not able to show here, but it started with SDR or single data rate. Then it evolved over various speeds like DDR, double data rate, then quad data rate, FDR, EDR, HDR, and currently we are at NDR. So NDR products are coming out, which means that you have around 400 gigabits per second of bandwidth over like a traditional 4x link. The current major deployments are mostly using HDR or HDR100. So HDR is basically 200 gigs and HDR100 is basically 100 gigs. So this is where most of the current deployments are taking place, but you will see that these adapters are already out and people are already trying to play around with that. So this is where the state of the art lies for IP. Let's take a look at the various components in the InfiniBand architecture. So you have what is called as channel adapters. And note that even though we are saying that this is for InfiniBand, the same concept will apply. The concept of a Q point or a end point is going to be applicable to all networks. Okay, whether it is Omni-Path or let's say Slingshot or whatever, you will have this concept of an endpoint. It's just that they would be called different things for different networks, but the fundamental concept would still be the same, and they would exist for all these kind of networks. So for InfiniBand, you have this concept of Q pairs, which are basically endpoints that application use to communicate through the network. And you will have switches and routers. So switches would be for intra-domain communication, and routers would be for inter-domain communication. And they may also support multicast. Similarly, you could have various other components, like you could have, you will definitely have your links. And in case you are going to span very long distances to make sure that your signal integrity is proper, you will also have repeaters. Now, links can be of multiple types. You can have your traditional copper-based wires or your optical wires. Now, the problem with copper-based wires is that because of physics, basically, after some point in time, you will have a lot of attenuation, and the length of your wires will be limited to a few meters. If you want to span, let's say, large distances across a campus or intercontinental or around the world, you would definitely need optical cabling. And that is where Intel tried to come up with this copper to optical conversion. So these endpoints that you see here are able to convert electrical signals into optical signals with very, very low, up to like 550 picoseconds latency. So this was something great that was done like a while ago. It is in use in some places, but mostly if you look at high performance computing centers today, they still mostly use copper cables, not generally optics, unless you have to span like very long distances. So let's look at the novel features of InfiniBand. So we'll start with the hardware protocol offload. So one of the major things with InfiniBand is that they try to offload the entire protocol stack onto the hardware. So the transport layer, the network layer, the link layer, and the physical layer. And again, the InfiniBand standard is several hundreds of pages long. So obviously, we will not be able to cover it in all that detail. We'll just be giving you a high-level overview of the basic communication semantics inside InfiniBand. Okay. So if you look at InfiniBand, you have a Q pair model where each QP has two queues, a send queue and a receive queue. It also has a completion queue. So whenever a work queue element or Wookie is taken from the send queue or receive queue by the InfiniBand device for processing, the result of that will be placed as a completion queue element or a cookie inside the completion queue. So at a high level, this is how your InfiniBand communication works. If an application needs to send or receive something, it will place it into the send queue pair or the receive queue pair. And once the operation has been processed by the InfiniBand device, it's going to place it back into the completion queue. And the application, by polling the completion queue, can understand what all operations that it posted has completed. Okay. So that is basically how the higher level works. So now let's start with the layers like the network layer and the link layer. So these have like various concepts, and we'll just highlight a few of the more important concepts here. So like we'll talk about like buffering and flow control, virtual lanes, service levels, and how quality of service is implemented using that, switching and multicast, and wide area network capabilities. Okay. So why do you need like quality of service? So if you look at it all around the world, you always have like differentiated quality of service. If you go to the airport, for instance, so you would have like different airlines would have like different medallion members, like let's say a diamond, platinum, gold, silver, bronze, so on and so forth. And depending on your let's say service level, the kind of service that the airline offers you would be different. So the higher medallions or the higher privileged customers will be asked to board first or like disembark first, while the others would have to wait. So similar concepts exist in networks as well, because certain clients would want to have higher service levels. Now in InfiniBand, you use the concept of virtual lanes, which is a hardware concept, and service levels, which is a software concept, to implement differentiated quality of service. Okay. So using virtual lane arbitration tables, which dictate how many packets should be processed from each virtual lane before moving on to the next, and service level to virtual lane mapping tables, one can implement a differentiated quality of service on one particular network. Okay. You can use this for like traffic isolation, traffic segregation, like and a lot of these things. Okay. So this is like fairly useful. The next thing that we'll briefly touch on is switching, or like layer 2 routing and multicast. So each port has one or more associated local identifiers or LIDs with it. So this is kind of loosely associatable with a MAC address. So the switches will look up which port to forward a packet to based on its destination local identifier, or DLID. Now this is populated on your switches by your subnet managers. And for multicast packets, obviously, since it has to be replicated or potentially replicated over multiple ports, it has a separate multicast group forwarding table. And if the multicast group you are sending to has multiple like egress ports, the packet is going to be replicated over all of those egress ports. Now, a switch itself is fundamental to the networking in InfiniBand, as with any network. The basic unit of switching is a crossbar. So it is literally all-to-all connectivity. It's very rich, and it is like fully non-blocking, which means that if any process can talk to any other process without interfering with their communication. Okay. Now crossbars will come in various form factors. So like earlier, it used to be like 24 port. Now you have gone all the way up to like 48 port switches. Now, your larger switches, or let's say your director class switches, or switches with like hundreds of ports, are typically built using this basic unit of switching called a crossbar. And they can be created in different, let's say, topologies. You could have like a fat tree, or a like partial fat tree, a dragonfly, like a 3D torus, or whatever. But once you create such a network, typically, these are called as non-blocking switches because basically of cost limitations. A crossbar is like really well provisioned, but if you want to create a crossbar network for a very large supercomputing system, it's going to be very expensive. So typically what people try to create are like non-blocking switches, where there is a potential of contention if your communication pattern changes. Okay. Now, how does the switching actually happen? So let's look at that with an example. This is a very simple fat tree with a bunch of leaf blocks and several spine blocks. We are taking the example of two nodes, let's say P1 and P2, who want to communicate with each other. And in this particular case, P2 has 2 destination LIDs or LIDs assigned to it. Now let's see what the benefit of this having multiple LIDs is. Now let's say when P1 wants to send a packet to P2, the packet is first going to hit its leaf switch. Okay. Now once it hits the leaf switch, there will be a lookup table there or a forwarding table there, which tells us in order to go to a particular LID, I have to take a particular egress port. Now let's say I am trying to send a packet with the LID of 2, which belongs to this node. Now it is going to go through egress port 1, then it will come down to this particular leaf switch and reach this node. Now what happens if this switch spine block goes down? If this is the only path that is available, then it means that there is no connection between these 2 nodes. However, if you have a second LID, then the subnet manager potentially can create a separate path to the network to this particular end node, and it can go through a separate one. So this is one of the benefits of having multiple LIDs assigned to each node on an InfiniBand network, assuming that your InfiniBand network is statically routed. Okay. So dynamic routing is very popular in the Ethernet world, in the World Wide Web. But even now, most InfiniBand networks are statically routed. Dynamic routing is definitely coming up. Various companies are bringing up solutions for dynamic routing. So once that happens, this equation may change. But if it is statically routed, having multiple LIDs does help with having redundant paths in the network from your source to your destination. Now, this work is done by the subnet manager, which is basically managing all the activities and ensuring that a particular network remains up and running. Okay. And the subnet manager may use different routing algorithms to give different paths. So this is your like unicast switching. Now let's take a look at how multicast switching works. Okay. So suppose this is an like imaginary network, and you have a subnet manager running on a particular end node. Okay. A subnet manager can also run on a switch, but typically for very large networks, we see that the subnet manager is run on an end compute node because it does a lot of route computation, which require a lot of compute and memory capacity, which is typically found easily on an end node rather than a switch. So the first thing that that would happen in a multicast is that a particular node would say that, hey, I want to join this multicast group. Can you help me do that? Once the request is received by the subnet manager, the manager is going to set up the multicast group in the appropriate switches. So it will say that, hey, the multicast forwarding table here, here, and here needs to be configured, so on and so forth. Later on, other processes can also join this particular multicast group. So now what happens is that if a multicast packet destined for that group comes to this particular switch, it is going to get replicated over these 2 ports, because this switch knows that there are processes listening in on this particular multicast group through this port as well as this port. Okay. So at a high level, this is how multicast works in InfiniBand. Very similar to how it happens on the Ethernet side. Now, we'll also talk about WAN. So when InfiniBand initially came about, it was meant to exist within a node. It was supposed to be an intra-node interconnect, as we talked about earlier. But later on, it kind of came out and became an inter-node interconnect, but still it was kind of limited because of various issues to within a particular room, or maybe a server room or a data center. So when people wanted to interconnect a lot of their InfiniBand clusters, which was probably spread across their local campus or across the country or even around the world, people began to come up with products which would create wide area network capabilities for InfiniBand. So there are optical switches from various vendors like NVIDIA, Mellanox, Obsidian Research Corporation, which allow you to extend the range of the InfiniBand over the internet, okay, using SONET connections or going over IP networks. Now let's go back and look at the transport layer. So there was a question asked earlier about queue pairs, right? How many queue pairs does a network card handle? So that's a very important question. So we are all familiar with the concept of cache thrashing at the CPU level, right? So you have a small cache. it is very critical that the application keep its active data elements in the cache so that it can quickly grab the data. The same concept exists for your network adapters as well. It has a small amount of cache which can hold control structures related to various queue pairs. Okay, the more control structures you have, obviously, just like the cache on the CPU, some elements may go out of cache, right? So that is when your performance begins to fall. So that is your fundamental equation. How much queue pairs do you need for communication, and how much can you actually sustain? Now, based on that, you have like various different protocols here. You have reliable connection, which has excellent features as far as communication offload goes, but it has a very high cost in terms of number of queue pairs to establish an all-to-all connectivity between all processes in a job. So it has m square into n queue pair requirement. On the other hand, you have unreliable datagram, which only needs one queue pair. But unfortunately, it does not have any of the nice features that the RC queue pairs offer. So this is fantastic for scalability, but not so good for performance. Okay. So people try to come up with a bridge, let's say, intermediate protocols where you can have the kind of features that RC offers, but with minimal number of queue pairs. Okay. So that is where protocols like extended reliable connection XRC or dynamic connector or DC, those kind of things came in, which kind of offers the full feature capability of RC with the scalability of UD. So this is these kind of connection-less protocols are where most of the let's say field is setting. So if you look at the EFA adapter, they have from Amazon. They use what is called as scalable reliable datagram or SRD. Okay. For their EFA network, and when SRD came out first, it only had support for a reliable datagram. It did not have support for RDMA. So later on, they introduced support for RDMA to make sure that your large message communication is also good. So as you can see, a lot of vendors are going to these kind of protocols where you limit the number of queue pairs each network adapter has to handle, while ensuring that they are able to provide good performance. Okay. Now, previously we talked about convergence, right? So this is what these two protocols are about. So your traditional sockets model kind of look like this. You have your socket SAP and your API. It goes over the kernel and then to the InfiniBand channel. So this is IP over IB. But the problem is that you have to go through the kernel for every single data transfer, which is not great for performance. That is where SDP or sockets direct protocol was used, where for the actual data transfer, you could have kernel bypass using RDMA. So this significantly improved the large message bandwidth. But the problem was that you still had to go from the user space to the kernel space, and this incurs a hit on the latency. So people try to kind of avoid that with various other solutions. So this is where RSockets came in. So RSockets tries to kind of intercept your socket calls and take it directly through verbs, thereby giving you good latency as well as good bandwidth for small and large messages respectively. So with the advent of these two protocols, your overall protocol stack looks like this. You had TCP/IP based applications on one end, RDMA based applications, or let's say verbs based applications on the other end. And you had these bridge protocols like RSockets and SDP, which allowed sockets based applications to get the benefits of the higher performance InfiniBand adapters. Again, this may not make sense currently when the concept of high-speed Ethernet is already there. But if you go back maybe like 15 years, when Ethernet was still at 1 gigabits per second and InfiniBand had moved on to like 2, 4, and 8, at that point, this still made sense. Okay. So now we'll go on to the high-speed Ethernet family, and I'll hand it over to Dr. Panda for the presentation.
Yeah. So let me just share my screen and then
okay.
see.
While Dr. Panda brings up his screen, any questions? So Dongla has a question. Static routing uses a single fixed path between endpoint LID pairs at any given time. Yes, it does. So with static routing in InfiniBand, it only uses one single path between two given LIDs at any given time. Now, if there is a change in the network configuration, that would like change. For instance, if a switch went down, then there could be some reordering that happens. But otherwise, there is only one fixed path.
There was not a question. I think there was an observation. Maybe you have covered this already.
Oh, right. So,
HPC.
right. So there was another observation. So HPC uses high performance computing uses photonic interconnects in the rack. Yes, silicon photonics is definitely coming up, and yes, it does use it for like long distance communication. Yeah. Thank you.
Can you see my screen?
Yes.
No? Okay.
It's perfect.
So so let's continue. So we looked at the InfiniBand. Now let's take a look at the high-speed Ethernet family, and then we'll take a look at how these two fields are converging. So we'll start with iWarp and then go into the others. So this iWarp, I don't know how many of you know. I mean, this iWarp actually started. I mean, if you see the terminology here is called Internet Wide Area RDMA Protocol. So once the InfiniBand started, gradually people saw that, yeah, Infiniband brought a lot of those RDMA and all those things, but these are mechanisms, and these mechanisms can actually be moved to Ethernet. Okay, so that was the kind of the very broad idea of behind the iWarp. So what we'll do is here, I mean, instead of again repeating everything for the iWarp, if you take a look at like the IB side and iWarp, we talked about some of these hardware acceleration, RDMA, atomic, multicast, congestion control. You'll see they're very similar across both. Only the atomic is not supported in the iWarp, and especially iWarp. In fact, the only current real product which is there from Chelsea. Some of you must have heard of this company. So they have actually is the Ethernet with RDMA. That is the iWarp product. Earlier there used to be a company called NetEffect. They also had a similar product, but that was acquired by Intel. And then Intel has its own newer product coming these days. So the major differences here, you will see there's a lot of similarity, but there are some differences in terms of data placement, data rate control, quality of service, and multipathing. So I'll be trying to touch some of these things. But before that, let's try to understand what that iWarp means. So, I mean, we talked about this TCP/IP stack. I mean, many of you must be knowing TCP. Then we have IP, device driver, network adapter. And then, of course, SCTP is there. So of course, this TCP, SCTP doesn't allow RDMA. So when this consortium, so this again, iWarp is a consortium, it is a standard. So when they started exploring that how RDMA can be brought, they brought three newer components here. These are like the protocol stack we're trying to take. One is the RDMA protocol, RDMAP, remote direct placement, RDDP. And then most important is this marker PDU aligned or MPA. So how these three things work together. So let's take a look at this, the challenges, and then the solution will be clear. So I think in one of the earlier slides, I indicated like with the one-sided operation, especially Mellanox Infiniband adapter, they provide very strong ordering. That means if I have a large message, if the last byte comes, I know that all the previous ones have arrived. But that cannot happen or is not expected to happen in the Ethernet world. You know, Ethernet world is very huge, a lot of different vendors, switches, and they are supposed to work together. So you cannot make like a one kind of design saying everybody has to follow. So that is the crust of the problem here. So if let's say the receiver is waiting, like a sender sends some 10 packets, might be it went through the network depending on adaptive routing, depending on fault tolerance, might be the 10th packet arrived first, followed by 5, followed by 7. It happened out of order. How does the receiver know where to place? Because it has to deliver to the application. If it doesn't place properly, then the application will get corrupted data. So that has issues of both from the application perspective. That means second half of the message has been placed doesn't mean that the first half of the message has arrived well. If in one message has been placed, it doesn't mean that the previous message has been placed. That is from the application perspective. Similar things happens from the protocol stack perspective. That means the receiver network stack has to understand each frame of the data. If the frame is unchanged during the transmission, this is easy. So to solve all these things, they introduced this MPA called
can you
marker
click on that
PDU aligned. So
sorry, can you click on that hide button next to stop sharing?
Oh, yeah, I
Thank
see
you.
that's coming. Yeah. So the MPA protocol layer actually adds the appropriate information at regular intervals to allow the receiver to identify fragmented frames. So what does that mean? So let's go back to the previous one. So what it does, let's imagine I have a pack, I have like a some 500 or a 2 megabytes of data. Most of the time, the Ethernet, like in the 1024 wide is the normal, the frame length. So what this marker PDO line does, before the application actually delivers it to the TCP layer, it adds some markers. And the way it was defined that in every 512 bytes, you will add some marker. So that means if I'm the header here, so this is the marker one, next 512 bytes, marker two, like this. So you have to do some processing. That's why iWarp will add some additional overhead based on whatever the lower layer provides. But once that marker has been put, if you do some little bit of analysis, you will see because the Ethernet is 1024 and we are putting markers in every 512 bytes. When I get a frame, it will have at least one marker. Okay, so that actually helps the receiver. So even if I receive the 10th frame, so it will have marker, it will tell, okay, now I put it on the 10th. Then if the 7th comes, then I put it on the 7th place. So like this will actually help me on the receiver side, and I'll wait. The adapter will wait until the entire thing comes and then give the message to the upper level stack. So that was the key things to bring actually the RDMA of InfiniBand or other networks to Ethernet. So this was the iWarp. So then the iWarp also has some additional, these are mostly from Ethernet side, like out of order data placement and dynamic and fine grained rate control. So this is a part of the Ethernet standard, not the iWarp. So especially those of you who are working on the Ethernet side, you will see that you can actually do dynamic bandwidth allocation. So that means if I have 10 gig network, I can actually put some stalls on every packet and then reduce that bandwidth to 5 gigabits per second. Okay, sometimes it may be a little bit complicated because TCP has windowing behavior and things may be different. But these kind of features are very important for environment of high latency, high bandwidth networks. Okay, please take a note. We are talking high latency, high bandwidth network, not low latency and high bandwidth. Okay, and these are especially transcontinental links. Okay, so like if we are sending messages from like Europe to Asia, Asia to Europe, those kind of things, there's a long latency involved. So if we allow the receiver to do the flow control, it's not good because a lot of packets will be on transit. I think there was a question earlier that if the receiver doesn't have the buffers, then what happens? I mentioned like all the packets will get dropped. There will be a RNR mechanism. Then credits exchange will happen, but that will lead to a lot of wastage of bandwidth. So that's why here, what happens, especially on this Ethernet side, it has the dynamic and fine-grained rate control. So large windows are exposed on the receiver side, and the receiver overflow is actually controlled to the sender side, the rate control. And iWarp also provides very similar, like we talked about, Hari talked about the bandwidth, quality of service, prioritization. It is very similar, just like Infiniband has service levels. iWarp also has 8 classes. You can define high priority classes, low priority classes. And more importantly, which is very unique to Ethernet world and also iWarp, which is not available in the Infiniband, you can request a particular bandwidth. Okay, so if I have a 5 gig link, I can actually request it exact like a 3.62 gigabits per second bandwidth. In the InfiniBand, you cannot do. You saw the earlier one, it is goes into SDR, DDR, QDR. You can always downgrade, but it is in some fixed intervals. It cannot be exactly a particular bandwidth. And there is actually some protocol called RSVP, just like we get an invite, and these days Zoom you say RSVP. That means you are providing your acceptance or rejection. Same thing happens this RSVP protocol. If I want to achieve a particular certain rate from a sender to receiver, and probe packet actually goes and looks at all the switches and see what is available bandwidth, and it tries to reserve that much protocols, that much bandwidth, and then in the end it comes back and says, yeah, now I have the entire bandwidth. So this is where this iWarp falls in. Okay, so if you see here iWarp, this is a little bit different than the TOE and all these R sockets, STP we just talked earlier. So iWarp actually sits below VERS. So if you see here, like between Infiniband and iWarp, it is the same interface. In fact, we'll see that in the software part of the slides just coming up very soon. That actually, in fact, when Infiniband came, there used to be a consortium called Open Infiniband or Open IB. But once the iWork came and started using the same verse, that consortium was changed to Open Fabrics, which is continuing. We'll talk about that. So that means anything you developed on top of it, like let's say our MPI stack, it runs transparently. It will run over Infiniband. It will run also on iWork. The only difference is that they follow very similar things. This is RDMA. It goes through TCP/IP. They both are user space protocols. Here it is iWork adapter, Infiniband adapter, and this goes with the Ethernet switch and Infiniband switch. Okay. So this is how like we have come. There is one more column left, and let's take a look at that. Okay. But before we go into that convergence, Ethernet has been there for many years. So there are also some vendor specific stacks. Okay. So we'll take an example of these two, datagram bypass layer and solar flare. Again, a lot of things have happened over the years, acquisition and all. So this the datagram bypass layer is very unique. I mentioned about this Miricom. If you remember, Miricom was one of the lead player in the cluster computing world. So later on, like actually once Infiniband, IORP, and all this came, they went down. But here, what they tried to do, that kernel bypass designs, like that low latency kind of thing, they try to apply to UDP. Okay, the unreliable datagram packets. Okay, so the idea was to bypass the kernel stack and give the UDP applications direct access to the network adapter so that you can get high performance and low jitter. Okay, and especially this is a primary motivation for financial market applications. And if you go to Wall Street and any big stock exchanges all over the world, they use a lot of HPC gears. Okay, in fact, there if you try to even to reduce like by few microsecond, millisecond, it leads to millions of dollars of profits. Okay, so the idea here is that think of like a, let's say the stock market. I mean, if some of you are familiar, I mean the stock tickers are coming, and you need to really try to make sure that you are getting those stock tickers with high performance, like with a reduced latency. But if something gets dropped, it's okay, because continuously it is coming like a stream. I mean, every second, every few seconds, the stock prices are changing, but I want to get it very quickly so that I can take a reaction. Okay, so that is where this is very little bit different than the traditional HPC market. So it's a timeliness is more important than reliability. Okay, whereas in the traditional HPC and all, reliability is very important. I cannot run a big scientific application where packets are being dropped and all. At an MPI layer, I had to make it reliable. Doesn't matter what happens below the network, but this is very different. And this stack is again not public. It is covered by NDA. Similar approach was taken by Emulex. Then similarly, also there was another company, Solar Flare, that also has been acquired recently. So they tried to they tried to use a hybrid kind of a design. So like we talked about this kernel bypass thing. So they wanted to come up with a protocol processing which can happen both in kernel and user space. Okay, and they also had internal protocol state shared between app and kernel using shared memory. So this is again a proprietary kind of solutions. But then for the last 7 to 8 years, another thing which has happened, which is the actual convergence between InfiniBand and Ethernet. Okay, and here we'll give two examples. One is a virtual protocol interconnect and RDMA over converged enhanced Ethernet, all called Rocky. So going back, a lot of InfiniBand adapters, including Mellanox, and that time I think other companies were there, Voltaire and all. They were coming up when the InfiniBand was coming into the market. A lot of deployments had already had Ethernet. So then the question is, are you trying to replace the entire thing, or can you coexist? Okay, so that was the whole idea of this, like introducing this virtual protocol interconnect adapter, so that one port, depending on the auto sensing, you can actually configure. It can actually work with InfiniBand or work with Ethernet. Okay, so for example, let's say data center. I think there was a question earlier. So if I am configuring the data center, might be the computation which is happening within the data center, they can go over InfiniBand. But the communications, what is happening to the outside world, they can go through Ethernet. Okay, so this is how these kind of things started coming up in the initial part. So data center with IB inside, Ethernet outside. And even in the earlier days, also Infiniband, because it has complex management procedure, people wanted to continue to use Ethernet management because that had a lot of Ethernet management ecosystem is very strong. A lot of tools are there. So this again allowed people to have solutions which can coexist. But then gradually we talked about Infiniband and iWork. We saw the verbs is same, but Infiniband has to use Infiniband switch, iWork has to use Ethernet switch. So that opened up a market. People had a lot of deployments of Ethernet switch. Then people asked questions saying, can I get the advantage of Infiniband or RDMA use with my Ethernet switch ecosystem, but not use iWork? Okay. And this is where Mellanox started entering the market, what they called like something called RDMA over converged enhanced Ethernet. Okay. So if you see here, this is like the Infiniband. We talked about IV burst, transport, network, Infiniband. So it goes up to here, but at the bottom layer, it changes to Ethernet. Okay. So you can think of it as like a Infiniband software with Ethernet hardware. Okay. And that actually a lot of users wanted to do that, so that they don't have to throw away their Ethernet switches, but they get advantage of not only the verbs level, all the upper level software, it can directly work. So in the beginning, they had only this. This was a Rocky V1, but then they still had some problems in the Rocky V1. Like it can still have things, but a lot of tools like these ACLs, snooping, network monitoring, they were not able to work. So that has changed. Now is the Rocky V2 has been introduced. So this is here we are saying Rocky, like is the Ethernet header, IB global routing header, and the IB header. So now they have actually put the UDP header also in between. Okay. So it started with Mellanox sells this Rocky, but now the big vendor Broadcom is actually adopting this. So Broadcom's newer adapters all are Rocky. Okay. So that Rocky ecosystem is also getting a lot of momentum, and of course we'll see it says like a Ethernet, so that the Ethernet environment is there. They can utilize a lot of existing software stack, and that's still at the same time you'll get good performance. Okay. May not be the greatest, but you will get good, better. And in fact, the last part of the section will show you some real concrete numbers, how these adapters deliver the performance. So wait for that section. So that now you can see the Rocky comes here. Okay. So there is no difference here. If you see, it's the same RDMA user space. Instead of Infiniband adapter, Rocky adapter. In fact, for Mellanox, to the best of my understanding, it's the same adapter, same hardware. They just make minor changes to the firmware so that it can actually work with the native Infiniband, or it can work with the Rocky. Okay. But of course, the Broadcom, they have their own Rocky adapter, and then it can work with the switch. And in this case, Mellanox also has entered the switch market. They also take their Infiniband switch and convert it into Ethernet switch, so that they can actually cover both the side of the market, Infiniband and Ethernet. So any questions here on this convergence? Any questions on the chat?
No, Dr. Panda.
Nothing. Yeah.
Okay. Okay. So with this, let me hand it over to Hari, and then he will continue on the Omni-Path, NVLink, EFA, and all those things, and then we'll come to the software solution.
Sure. Hi guys. So we are kind of heading to the like last stretch, here where we talk about the various interconnect architectures, and then go into the other hands-on exercises. Okay. So we'll talk about Omni-Path first. So Omni-Path has had a very rich evolution, so to speak. So it started off a long time back in 2003 as a company called PathScale. So they used to create PathScale products. So there is a question from Suresh. Can the same Mellanox switch work for both IB and Rocky too? I believe so. So you can change the switch's configuration to IB or Ethernet in the management infrastructure. I believe they have the capability where some ports can be IB and some ports can be Ethernet, but I'm not entirely sure about that.
Yes. So just to add there, I think In fact, Mellanox sells some of the switches. If you remember the, like, let's say take FDR, it has 56 gigabits per second, whereas Ethernet world it is 40. So they call it, okay, we can give you a switch which is Rocky compliant, but it will be higher bandwidth than the standard Ethernet switches. Because Ethernet switch you don't get for 56 gig. But because they're using the same hardware with some changes to the software and firmware, they can actually deliver higher speed compared to regular Ethernet.
How often do you see 12x IB used? Not very often. The reason
No.
is that if you see 12x, like you see the cable will be about that thick. So literally, it will break your your NICs endpoint. Just it will literally snap it off. So typically, you don't see 12x. I mean, I believe a long time ago people have tried to use it, but mostly it is 4x cables. That is, so your 4x cable is the width of your pinky. Like your 12x cable is about that thick, which is not very feasible in real life.
Yeah, so that was the IBM's product. It is dead. Nobody's using those things.
Sure. Again, thanks for the questions, guys. This at least gives us the feeling that you guys are awake and listening. Thank you. So Omni-Path started as part scale like a long time ago. Later on, QLogic enhanced the product with the PSM, or the performance scaled messaging software interface. This was later acquired by Intel and rebranded as Omni-Path. That lasted for some years, but then Intel declared it as end of life and spun off a separate company called Cornelis Networks. And they are continuing Omni-Path as Omni-Path Express now. So this is like a brief history of Omni-Path and how it has evolved over the last several years. Okay. So the Omni-Path has a very, sorry, Sudhir, you had
just sorry to interrupt. There was one question on the Slack. I can read that out.
Oh, okay.
With the convergence of IB and Ethernet, example Rocky, the usage of individual lane, either physical lane or virtual lane, stays the same as before, right? Maybe you want to. Can you see the?
Okay. Actually, okay, I see. I think Sissy Yuan has changed. So with the convergence of IB and Ethernet, the usage of individual lane, either physical or virtual, stays the same as before. Right. So on the Ethernet side, you don't have the concept of virtual lanes to implement quality of service. So it's implemented in a different way. So the way like quality of service implemented on both sides are different. So it doesn't exactly stay the same between IB and Ethernet. Okay. I hope that answers the question, Sissy. So coming back to Omni-Path, so it has a very similar protocol stack like Infiniband. So they all introduced a layer 1.5, which is called a link transfer protocol. They have to, when Omni-Path came out, they tried to make it much better than the existing Infiniband standard. So they added like support for a larger fabric addresses, larger payloads, and different kind of other mechanisms in the various layers. They also increased the number of virtual lanes. So the Infiniband standard provided for like 16 virtual lanes, which is like 15 for data and 1 for management traffic. Omni-Path bumped that up to like 31 data virtual lanes and 1 for management. So they had like a similar policy for like ensuring the credit-based flow control. They could also use these virtual lanes and traffic classes to create what is called as different partitions in the network. So this could be thought of in a loose sense as your VLANs in the Ethernet world. So where you try to restrict the access that a particular node has to other areas of the network. So Omni-Path provided the flexibility to partition your network in different ways. So one node could be part of multiple partitions, or even all partitions, depending on how the administrator chose to do it. So this is some example of that. And they also have like a very rich transport layer at the layer 4. So the fabric had like support for all different kinds of higher level applications, including your like message passing interface applications, SMEM applications. And the underlying hardware was exposed through two different interfaces. One was called the performance scale messaging or PSM interface, which several years ago, PSM or PSM2, which was particularly designed for HPC needs. But over the years, they have slowly migrated away from PSM, PSM2 and PSM3 to the Open Fabrics or OFI interface. Now, there was a question earlier about what is NVLink, what is UCF, and things like that. So NVLink is a hardware concept. UCF, UCX, OFI are like APIs or like software concepts, which kind of provides a bridge to the hardware for higher level applications. So Omni-Path Express, as well as the later generations of Omni-Path, did provide an interface through the Open Fabrics interface to the underlying hardware. So the benefit of OFI was that it was more suited to express various communication requirements that the application had. Okay, and this was designed by a large alliance of people in the community called the Open Fabrics Alliance, or like OFA. So now when we combine all of this, you have a large slide here showing how the various transport protocols evolved over the last 20 years and what maps to what underlying hardware. Okay, so if there is anything that you would like you to take away from this tutorial, it is this one slide. Okay, in the future, if somebody says that I have this product which goes over this protocol, or this protocol that goes over this product, you can just refer to this one slide and you can figure out, okay, what exactly is happening. So there was a question about CXL. So I think this was also mentioned earlier. So this is an upcoming feature in the community. CXL is coming up. So we are still trying to see how CXL will fit in the overall picture. So far it has been like an intra-node interconnect. So we'll see probably in the next year or so, we'll see how it evolves out, and we'll try to add that. So what is the physical layer for Omni-Path, QPI, PCIe, Ethernet? So it's very similar to Infiniband. The physical layer for Omni-Path is very similar to Infiniband. So it is not QPI or PCIe. Those are intra-node interconnects. And it is not like Ethernet either. Okay, so it was more like Infiniband, so to speak. Now, if you look at more of the newer network protocols like Google Aquila or Slingshot 10 and 11, they are heading towards Ethernet. So they are heading towards Ethernet-like protocols, or as Slingshot brands themselves, like high performance Ethernet or Ethernet for supercomputing, like whatever you want to call it. So there was another question about security and privacy vulnerabilities for CXL. So we have not looked into that. So people are still kind of researching into that. But in general, let's say, even if you look at verbs or OFI, security has not been a real consideration when they designed it. So all of these were designed to be in physically secure locations where they did not expect bad actors to be that prevalent like they are in the wide area network. So this was never a concern. Actually, there are a lot of publications from researchers highlighting very simple security vulnerabilities for all of these protocols. So if you're interested, please ping me. I can point you to those papers. Yes, so again, people are trying to address this. There is a lot of research in this area where they say that, for instance, if you do snooping on the network, you could get the like a remote key, and like if you are a bad actor, a lot of bad things can happen. But the reason why it has not been a big issue is because these protocols have not really made it out to the big bad world of the internet. So far they are in a like a data center where the access is very limited. You vet the people who you give access to the cluster. So there is a different level of security. That's why these have not become huge issues. Yes, and I definitely agree. There is a huge opportunity here, and it is an active area of research. However, we have not seen a lot of products come out in this area till date, probably because there is not enough demand on the consumer side. So thanks again for all the questions, Pai. So in this slide, we compare the various features of InfiniBand, high-speed Ethernet, Rocky V1, Rocky V2, and Omni-Path. So as you can see, they are almost like mostly similar, except for minor differences here and there. And this also you can use as like a reference architecture. So Donglai had another question here. Only Omni-Path supports OFI? No. So OFI is a higher level application programming interface. It has different underlying providers. Okay. So for instance, there is an Infiniband provider for OFI. There's an Omni-Path provider for OFI. The EFA adapter from AWS has a provider for OFI. So like when we go later down into the software stacks for commodity high performance networks, basically here, we'll talk about how all of these kind of tie into the hardware ecosystem. Thanks for the question, Dangla. So now we'll talk about the NVLink and the NV-switch interconnect architecture. Sorry, there was a word missing here. So NV-switch should be here. Sorry about that. So as Dr. Panda mentioned, there was a reason why NVLink and NV-switch came about, because NVIDIA felt that they were not able to get the kind of performance they need to keep their GPU units busy all the time. Okay, so as a result, they began to introduce different kind of interconnects to bridge their GPU devices. With each generation of newer GPUs, the communication capability of the NVLink also increased. So with the latest V100, A100, or H100 devices or GPU device from NVIDIA, you have close to 300 gigabytes per second of communication bandwidth per link. Okay. So initially, when the interconnect was brought out, it came out as a point-to-point interconnect. So each GPU would have a fixed number of connections, maybe like 4 or 6 or some number, and they would take those connections in some topology and make sure that you have some sort of all-to-all connectivity using one hop or more than one hop inside the node. Okay. And you also could have NVLink to the CPU. Okay. So if you look at x86 kind of architectures, the only way you can go from CPU to the GPU is through PCI. So you could have like PCI Gen 3, Gen 4, whatever there is, but you could only go through PCI. But that is a bottleneck. So what IBM and NVIDIA tried to do was they tried to see if they could have NVLink enabled CPUs like the Power 8s and Power 9s, where the GPUs could use NVLink to talk between themselves as well as to the CPUs. Okay. Now, this led to a lot of high performance solutions that could be designed between the CPU, the GPU, and the others on the system. Okay. Now, the problem with just using NVLinks is that after some point in time, you really can't scale out. So that is when people from NVIDIA began to think of more of a switch kind of topology, and they try to come up with what is called as NV-switch. Okay. Now, if you look at NV-switch, you could it was capable of connecting up to 8 GPUs. Okay, so this is again like a full crossbar within a baseboard. So the NV-switch topology had like 2 baseboards. Each baseboard could connect up to 8 GPUs. And you had like 300 gigabytes per second of GPU to GPU bandwidth within the baseboard. Once you go across baseboard for inter-baseboard communication, you had about 2.4 terabytes per second, or basically 25 gigabytes per second per link in each direction. Okay, so within one baseboard, it was fully like non-blocking. It was a crossbar, but across baseboards, you could have some sort of contention that is occurring. Okay, so now imagine one compute node with 16 GPUs or 16 H100 GPUs or A100 GPUs with NVLinks connecting them. That is an awesome amount of computing power that you have. Now, the other problem of such architectures is that you are in a sense creating islands of computation. Okay, you have these huge islands of computation with teeny weeny links going from one computer to the other. So this is going to be a big problem if you really want to scale out to like maybe hundreds of nodes. And this is where the DGX2 kind of architectures come in, where the system has the ability to have 8 different HDR or NDR adapters. So those kind of systems will kind of provide a balance between intra-node communication bandwidth and internode communication bandwidth. So we always need balance to make sure that you're able to scale out to many hundreds of nodes. So we'll look at the EFA interconnect architecture from Amazon next. So there was a question. PCI can also cause loss of data versus NVLink. So do you mean the amount of control information that is required for each data frame that is sent out? Or do you mean like a UD kind of loss of data? So while Pi comes back on that, I can continue. Amazon has been working on their EFA adapters for a long time. Now, one of the primary things with Amazon is that Amazon is known as a huge e-commerce vendor, right? So they make a lot of money from that. Now they're going to plug in their high performance solution into that like data center. So one of their biggest concerns is this: just because I'm plugging in my HPC system into my data center, it should not hurt all the other traffic that is going on there. So one of their primary concerns was to make sure that they could have ECMP multipaths through the network so that we don't create hotspots. Okay. HPC by nature is communication intensive. You could have a lot of communication happening, a dense communication happening. And if this is going to create hotspots in the network and affect their other traffic, that'll be very bad for them. So one of their primary goals was network aware multipath routing to avoid congestions or hotspots in the network. To achieve this, as I mentioned, they introduced a new QPair type called Scalable Reliable Datagram, or SRD, and they did not have support for RC, okay, because they basically wanted scalability. Okay, they wanted to make sure that their data could be rerouted anywhere through the network, and it would not cause hotspots in the network. They want to make sure that their existing data center would not get affected because now you are adding this HPC into the mix. So actually, Saurav here was the person who did the initial work while he was working with us a few years ago. So this is a comparison of UD and SRD. So one of the main differences is that we have reliable delivery with SRD, and we also have an increased like message size. So with UD, you could only have 4 kilobytes. With SRD, you can have 8 kilobytes. Now this table is actually not correct. Now SRD does have support for RDMA get operations. Like RDMA read operations are currently supported with SRD, which gives much improved performance for your large messages. So this has to be, let's say, updated. So now SRD does have support for RDMA read. This was introduced maybe about 6 months back in the OFI by Amazon. So there's another question from Suresh Singh. Is NV switch used for connecting GPUs only within a server or connecting GPUs among several servers? Currently, NV switch is within a node only. It is not inter-node. It is only intra-node. So let's go to the next architecture, like the slingshot interconnect architecture from Cray. So slingshot is HPE Cray's 8th generation scalable interconnect. So with each interconnect, there was some particular problem that they were trying to solve. So one of the most important challenges, as Steve Scott addressed it during his Hexacom keynote talk, was ensuring some of these features. So it should be Ethernet compatible. Okay, you should be able to easily bridge it to other Ethernet networks. You should have the ability to recover from network congestion very quickly. You should be able to limit network congestion. You should be able to recover from it very quickly. You should have efficient congestion control, and you should have very good tail latency with low jitter. So this was some of the design goals that they had when they tried to come up with the slingshot interconnect, as pointed out by Steve Scott during his Hexacom 19 keynote talk. So their switch was called the Rosetta switch. It has a 16 nanometer form factor with several ports, and this is how the tile looks like. So these switches could be connected up in different kind of topologies. So this is one depiction of how this could be connected in a dragonfly topology. And you could have different kind of topologies. We could have fat tree or anything else for intergroup or intra-group communication. So there are different ways of putting it together. Now, one of the, as I said, one of the most important factors was to have quality of service, like different quality of service classes, and ensure that that is strictly adhered to, and that you are able to quickly recover from congestion events. So this is something that Cray HPE spent a lot of time on, trying to make sure that you're able to prioritize traffic into different classes, and one class does not affect the other. And even if a congestion event does occur, they try to come up with a new benchmark. I don't know if you guys are familiar with the GPC net benchmark. So that was introduced by Cray sometime back. I think they submitted as a paper to the supercomputing conference like a few years ago. So using the GPCNet benchmark, they were trying to evaluate how much congestion happens in the network and how quickly you can recover from them. And those studies kind of showed that Slingshot 11 is able to very quickly recover from congestion events and make sure that it doesn't affect the traffic for a long time in the network. Now, Sissy has a question. In this NV switch topology, how much power is spent on the IO network? There is no study on that yet, Sissy, but in general, what we have seen is that the network tends to consume around 5 to 10% of overall power on the system. So the amount of power consumed by your communication fabric is typically not that high. I have not seen any studies analyzing how much power is actually consumed for an intra-node network like NVLink to move data. I don't even know if there is a way to measure that. Okay. And I hope that answers the question. So we'll move on to the Fujitsu Tofu interconnect architecture. So this is a proprietary interconnect from the Fujitsu Corporation in Japan. This has been powering the K supercomputer and the Fugaku supercomputer over the last several years. So Tofu stands for torus fusion. Okay. So basically, it's a torus of torus. So they have like two torus networks connected up. So this is how the larger level torus looks like. They have like 3 dimensions, X, Y, and Z. And each element in the larger level torus is a small torus with 3 dimensions, A, B, and C. Okay. So overall, the cluster will look something like this. Each compute element in this smaller torus will have connectivity to communicate to all the different dimensions. Okay, so your Tofu network interface or TNI looks something like this. So as you can see, it has like different links, and each link goes to a particular dimension in the torus. So you have different RDMA engines fueling these or driving these links as well. So as you can see, like some of these links go in the XYZ direction as we saw here, and some of the other links go in the ABC direction as we saw in the slides. Okay. And you have specific support for collectives in the Tofu network interface, and you can offload certain collective operations to them. Now let's compare different generations of the Tofu interconnect. So like generation 1, generation 2, and like the 3rd generation called Tofu D. So this slide kind of does a objective comparison of these on various metrics like data rate, number of signal lanes per link, bandwidth, number of the network adapters available per physical node, and the injection bandwidth. So as you can see, between Tofu 2 and Tofu D, even though the injection bandwidth reduced, the number of interfaces kind of increased. So this allows the Tofu D to simultaneously transmit in multiple directions and get overall improvement in performance. So much so that it is approximately twice of Tofu 1 or Tofu 2. Okay. Now, Tofu also has support for dynamic packet slicing. The physical layer is independent for each. So basically, you can split up the packet into smaller slices and send it through different routes. So it can also help with detecting errors and detecting them and correcting them. So these are some advanced features in Tofu. So Tofu also has, as I mentioned, a lot of resources for offloading collective operations. So this is very critical. So if you look at the older generation BlueGene kind of networks, they had three separate physical networks, BlueGene. They had one network purely for barrier, they had one network for reduction, and they had one network for all other communication. So because of this, because they had three separate physical networks, BlueGene could perform microsecond level barriers at the entire system scale. So this was a fantastic system. So IBM put together all of the system in such a, let's say, tightly integrated manner that the system would work very well together. So similarly, Tofu has support for increased barrier resources. So a lot of high performance networks, for instance, Infiniband has support for collective offload through SHARP, scalable hierarchical like aggregation protocol. Similarly, Tofu has support for offloading like barrier operations, and this kind of lists the amount of resources available in the network. So Dongla has a question: why 10 ports in Tofu switch and not 12? That I'm not sure. So that's probably a question for I think our friends at Fujitsu. So I'll probably have to check with them and get back to you on that, Dongla. So now let's look at Google's Aquila interconnect architecture. So this is like a brand new, like hot off the press, so to speak. So this was based on a paper that Google had published at Usenix some time back. So this is also based on based on Ethernet. So even though it explicitly doesn't run on top of Ethernet, but it is kind of sort of very similar to that. So it has a cell-based layer 2 switching protocol. So a cell is smaller than a packet. So the claim is that it leads to better and deterministic performance and a lower latency. It has optimized for small units of data commonly used in RDMA. It uses a converged network functionality with top of a rack switch plus ASIC plus NIC. So it uses another protocol called GNet and an RDMA variant called 1RMA for communication. So their paper shows that on average, for about 1,000 node cluster, you can get a 4 microsecond remote memory access performance between any two nodes on the system, which is pretty cool. So Google introduced something called TOR in NIC or TIN. So it is a single chip with both NIC and switch functionality in the same silicon. So it's a medium radix switch. It's not like a high radix switch. It's a medium radix switch. So it adds like a NIC and switch combination with a modest increase in cost. So all of this is kind of wired together via a copper backplane in like a big pod. So this kind of ships as a like a rack level unit, and an enclosure the size of a traditional top of the rack switch. Now, with this kind of an architecture, the servers can directly connect to the pod via PCIe and get the NIC functionality. Okay, so that is how this works. Now, the way the TOR and NIC or TIN works is that it has a pair of PCIe 3.016x slots and one really big 2 to 6 gigabits per second pipe into a single server, or like that can be split as two separate pipes for two servers. The other side of the PCIe Express switch is a pair of network interface circuits, one that speaks 100 gigabits per second IP and which can go to Ethernet. The other, which speaks their proprietary 1RMA protocol and hooks onto the GNet cell switch. So if you look here, you have all of these here. So you have the GNet cell switch here, the 100G IP network here, the 1RMA NIC here. So this is how your overall architecture looks like. So basically, once your packet gets here, you can go over Ethernet, you can go over GNet, you can go over PCIe. So it kind of is a one-stop shop for accessing different networks. And the cell switch has 32 ports running at 28 gigabits per second each. With the encoding and the overhead taken off, these cells can run at about 25 gigabits per second of data rate. Okay. So this is the same speed as IBM's BlueLink, the OpenCAPI ports on the Power9 processors, as well as the NVLink 3.0 pipes in the A100 GPU. So this is just mentioned here so that you have an approximate idea as to the performance. So just so that you understand that it is not like very slow compared to others in the ecosystem. So you have several of these links that are used to connect all the servers in a pod over to others. Now, these pods can be connected to form larger groups called cliques, and different kind of topologies, for instance, like a dragonfly or a slimfly or anything else, can be used to connect all of these into like groups of pods. Okay. So overall, the Aquila fabric would look like this. Like it has a very fast Dragonfly network inside of its data center scale class network, and it is based on a leaf spine topology that is not an all-to-all network, but it does allow for everything to be interlinked in a cost-effective and scalable fashion. So I think previously somebody mentioned that photonics are also used in like HPC as well as data centers. So this optical links allows for Aquila pods to be up to 100 meters apart and only impose a 30 nanosecond per hop latency between the interconnect pods. Okay. So the switches themselves have a multi-core 64-bit processor with 8 to 16 gigs of memory. It uses software-defined networking or an external SDN controller to perform local compute on the Aquila chip package. So this is typically how Google envisions that these kind of let's say Aquila pods can be deployed. So they envision that we could have two 24 server pods in a rack and 24 such racks in a click. And the NICs can be placed on PCI adapters that links to a switch chassis that has a dozen of these tin ASICs on like different adapter cards. The first level of the Dragonfly can be directly implemented in the chassis backplane itself. And you could have different number of GNet links coming out of the pod to connect the pods in either in an all-to-all fashion or with anything else. So with this, we kind of come to the end of the overview of different high-performance networking architectures. And I can hand it over to Dr. Panda for an to discuss the overview of the software stacks. So while Dr. Panda like begins the screen share, are there any other questions? That's okay. So there's a question from Peter. Does fiber channel fit in here at all, or is that different? So you could have fiber channel over Ethernet here as well. So in fact, Mellanox has some products which converts InfiniBand to fiber channel over Ethernet and back. So they have what is called as virtual protocol interface or VPI, which allows us to do these kind of exchanges from one one network to another. So yes, fiber channel can be fit in here, and it can quite easily interact with high performance networks like InfiniBand, Rocky, and even Omni-Path. I hope that answers your question.
Okay. So Hari and all, can you see my slides?
Yes.
Okay. So we got exposed to a lot of these different kind of networking architecture. So now let's take a look at some of the software stacks. And as you saw, like some of these are like let's say Tofu, Clingshot, Aquila. These are like a proprietary. So I mean, these are many times you don't know what is happening. So from the software perspective, we'll at least focus on the commodity ones, like the Infiniband, IWARP, Rocky, Omni-Path. So to give a historical perspective, I mentioned this a little bit earlier. When Infiniband came in the 2000, there were a lot of vendors. They were producing different hardware components. But then the US Department of Energy, or the DOE, they are like one of the largest customer of the HPC systems. They asked all the people to come together to define it like a standard or some kind of a software environment. So it was known as OpenIB. But then when the iWork came, like Netify, Chelsea were there, so they also were brought into that consortium kind of thing, and it was renamed as Open Fabrics. So, so the idea was to design this just like Linux kernel. You know, the Linux kernel, I mean, there is a worldwide community, people develop periodically. I mean, it's continuously it is being tested, and periodically the different distros like Red Hat, SUSE, and all download the version, and then they get deployed. So they adopted the similar model for both for support Linux and Windows, and and that is called like the through that there was a OFED got developed called Open Fabrics Enterprise Distribution. Some of you must be here knowing this. And then it was very successful for many years. In fact, from even OSU side, MHAPIS 2, we are a part of that stack, even OpenMPI. So they brought multiple MPI providers so that you get complete stack and you just download and then. So it went up to certain extent, but then again, just like I mean, we talk about hardware and then different business practices, some kind of frictions started a few years back. And especially like let's say Mellanox was putting InfiniBand, broad newer features were coming, so they were not being merged in a timely fashion. So then Mellanox went ahead and they created a version called MoFed, Mellanox OFED. That's what you see a lot of InfiniBand deployment, and then similar, and then it got even split further. I'll talk about that in the next few slides. So so far, like it still says Open OFED 5.3. If you go to the Open Fabric stack, you will see like that is the kind of the latest. This is the latest stable release 4.17 of DAS, but the 5 series is just mute kind of things. But it has a very nice idea. So let me explain those ideas. So the idea was that we talked about all these horse interface, and every vendor who wanted to contribute their adapter, let's say you are a vendor X and you are designing your adapter, they ask two components to be added here. So like for example, IBM has its adapter, ESC adapter, so they will contribute a kernel module, they will contribute a user module. Similarly, MLX contributes one module here, one module here, and then it was standardized so that altogether any user can actually select the OFED stack and below they can use any adapter. So it was good actually for end users. It was also good for industry people because you don't have to continuously test. I mean, if you, let's say you are a company, you are coming up with a newer network adapter, you have to test the entire software stack. That will be very hard here. Whereas here, this software stack has been standardized, so you get the benefits of all the upper level software stack. It could be MPI, file system, everything is there. As soon as you contribute these two and make sure the basic verbs work, everything else will work. So even the Open Fabrics, they spend a lot of time in unifying all these different components. The left hand side is InfiniBand, right hand side is Ethernet. We talked about some of these things earlier, like IP over IP, SDP, SRP, UDAPL. So they try to put it together. But then what happened? It got split. And this is what you see currently. The standard Open Fabrics enterprise distribution is dead. But then there are two competing software stacks are evolving. One is the UCX, which is being promoted by NVIDIA, which acquired Mellanox. So here below, if you see the UCX stack, so they are trying to bring CPU, GPU, all these other, even the MPI, PGAS, other modules, bus buffer. So they are trying to put on top of it. So below they have like a UCP, then they have a transport layer. So that thing is going on, and they have formed separate working groups: UCX, UCC, OpenSnappy, Spark UCX, Advanced Data Type Engine UCA. There is some benchmark. It shows some like a release schedule, so they have public releases kind of things. And this is primarily now being geared towards InfiniBand and Rocky. Okay. On the other side, I think Intel from that basic Open Fabrics, it migrated something called to Leap Fabrics. So here they put a little bit different perspective in the sense, if a vendor comes up with a NIC, what they need to do is like they need to provide something called a OFI provider, Open Fabrics interface provider. And then they also try to standardize something called from the top called Open Fabrics interface or OFI. And between these, there are a lot of queries kind of things. And it's a little bit modular architecture. So the idea is that if let's say the MPI wants to run on some NIC, they have the top level interface OFI, which is standardized. But then what services are available here is based on provider. The provider may say I have XYZ but not W. So based on that, the appropriate Wi-Fi interface will be triggered. So that is the kind of a little bit of philosophy behind the leaf fabrics. And so here again, it wants like any upper level developer should just use Wi-Fi. And in fact, if needed, even some provider can actually keep their code very um, constrained kind of things and even not make public. Even the UCX people are also advertising the same thing, saying if you have an upper end application, you just remain at this layer. You don't go below and they will try to work on. In one way, it is good, like a productivity point of view, if you are a designer or developer of the upper software stack, but then you get sometimes stuck. If let's say some performance X is not good, you cannot change it. Okay. Whereas the earlier approach was that people were able to go to the very lowest layer, which was worse. So alternative designs were there, and then as long as you understand the verbs, you should have a lot of flexibility. So these are the kind of the two directions are going. There are different camps are being found. Like let's say Cornelis network we talked, they are going through Wi-Fi. Slingshot is going through Wi-Fi, but whereas the Mellanox, Infiniband, Rocky, they are going through UCX. I believe Intel is also going through their Ethernet adapter through Wi-Fi. So like this, we are seeing these communities. Both the communities are evolving. We don't know how the future lies, but we have to keep an open eye and then see what is going on. So that is like the software. Now let me take a look at the train. So this again, I'm taking some numbers from the top 500. As you know, they have a lot of this data on the website. So they mentioned something called Interconnect family share. So some of you might have seen this like a pie charts. This is the left side is based on count, like out of 500 machines, which technology is being used on how many machines, and the right side is performance, like the aggregated performance. So before June and after June, a lot of things got modified. The June, as you know, the Frontier um, uh, exascale computer from Oak Ridge was announced, and it is, even though it is a slingshot, they actually exposed, say it is a Ethernet. So that's why you see this big number has come. Actually, one machine has actually, and some other machines have also added to this one, and also under this gigabit Ethernet, all those Rocky other systems also come into play here. So currently Infiniband is like a 39%. I'll call it Ethernet. They have not changed the name. It's still on their database. It says gigabit Ethernet. It doesn't have to be 1 gigabit. It can be 100 gigabits, 200 gigabits, or 400 gigabits. Then Omni-Path is here. Then there are some proprietary networks. This is like the Fugaku, Tianwei, Tianhe systems like that. And the performance, that's what has also affected because of the number one system is coming over the Ethernet. It's putting a lot of weightage onto the overall performance side. Here it just shows like these are from the June 2022 list. As you can see, like there are around 230 IB clusters, installations in the top 50 are these are just reference. You can take a look at later on. This is also like the Ethernet kind of things. There is a small typo here. Sorry, this should be June 2022. So this is the Frontier. As you can see, it's 8.7 million cores that is using Slingshot 11. So there are some of the Slingshot 11, Slingshot 10, several of them. And then it goes into even some of the cloud providers and all, like Amazon EC2 and all, they are listed here. So like this list goes on. So that shows you, give you a little bit of perspective of the software stack. So now let's take a look at some concrete numbers. Okay, because we have been talking about a lot of performance, but just to get some idea. So what we have done here, we have organized at two levels. One is the low level performance, that's the network level. And then one such middleware, which is MPI. We are more experienced with that, so we'll present those numbers. So here, if you remember it, we talked about this Infiniband and Rocky. So these are numbers are taken. I mean, the below are the details. These are all different environments we have in the lab. So we have taken these numbers, like this Haswell Intel back to back with EDR and Rocky. So as you can see, like it's basically the same adapter. As I said, like in the Rocky mode, you have a little bit of overhead. So this is like a 730 nanoseconds. So this is like a node to node and with a back to back. Okay, so we don't have like sorry, yeah, this is a back to back. So there is no switch or anything is involved here. So you see around like 130 nanosecond overhead when we go to Rocky, um, and the large message latency again. The once you go to very like a 1 meg, 2 meg kind of things, the higher bandwidth you have. I think in this case both bands are same, but the InfiniBand gives you a little bit of benefit. If you see the unidirectional bandwidth we talked about, they are again very similar, um, because Ethernet has that limit. InfiniBand goes a little bit up. So here you get like a 12.4 gigabytes per second versus 11.5. Now, if you compare like we talked about some of the sockets, R sockets and bursts. Okay, so there is a clear difference. So here you can see, so this is like a similar system here. The sockets has a lot of overhead. This is what we talked in the very beginning. If you see here on these machines, it's like a 5.94 microsecond. Whereas below, if you see the R sockets, is that RDMA enabled socket, so it is able to come very close to bursts. Uh, and that is good for many applications. You may not see all the features. I think Hari mentioned like with R sockets, but if you are running like let's some big data workload or some workload where you did not need all the functionalities, you should be good with R sockets versus sockets. Because the sockets also you see the latency goes very up, and the reverse is true for the bandwidth. Here you can see like the InfiniBand is at the top. Even for the intermediate message sizes, it rises very fast. Our sockets is somewhere in between, and then the sockets, the traditional sockets is very low. We talked about the EFA. These are some of the numbers we have taken on the AWS EFA. Here you will see one interesting thing. You will see, uh, I mean, they wanted to, as Hari indicated, like they wanted that multi-path kind of environments to blend well with the data center, but the latency is very high. You see, in all the other network, we're talking about 1 microsecond, 2 microsecond, but here, if you see, the latency is like a 15, 16 ping pong latency. And we talked about these two, UD versus SRD. So here you will see the SRD is giving a little bit higher overhead. The message rate, also the UD based designs gives better unidirectional, bidirectional bandwidth. And this is the Broadcom Rocky adapter. If you take a look, these are the IB send latency, the Rocky and InfiniBand, they use the similar kind of with the burst. So it is around 3.37 microsecond. And this is on their 100 gig adapter linked with the AMD platforms. And here you can see like a bandwidth wise, it is coming out very good. It's like 1162, and then the bidirectional is 23. So coming very good, close to 100 and 200 gigabits per second. So then if we go into one of the upper layers, I mean, here we'll be talking about some of the things called in the MHAPPIS project. I think some of you might be familiar. We have been doing this from the day one of InfiniBand. When InfiniBand came in October 2000, we were the very first one in the group, in the world, to jump in and design an MPI library. So that is the MHAPPIS library. We had, in fact, first open source version demonstration at Supercomputing O2 almost 20 years back. So since then, continuously, we have been enhancing with different versions of the MPI standard, all the different networks. So now we support all the networks. In fact, we just made a new release just a few weeks back. So we support even Slingshot 11, Broadcom, Rockport Network, so Intel adapters, so all the commodity things. Not the proprietary, like we don't have a version running on Fugaku or tofu, those kind of things. So currently this tax is being used by more than, you can see, 3,000 organizations in 90 countries. Just from our website, we are hitting like a more than 1.6 million downloads. And that is just from our website. Of course, our stack is available with a lot of other software stacks and distributors like Red Hat, SUSE, OpenHPC, even SPAC, and a lot of top 500 clusters all over the world actually utilize our stack. So I'll take some sample numbers using this MHAPPIS2. You can, if you have any other favorite MPI library or any other stack, you can do the similar evaluations, okay, just to see the trend. So here we have listed some of them, like a starting from like a TrueScale, which was the prior to Omni-Path, ConnectX-3, ConnectX-4 up to ConnectX-6. We just got some ConnectX-7 hardware. We have not been able to run it as of today, but we will be able to happy add all these numbers in future presentations. So broadly, if you see, there is a small message latency, like half of round trip. So at an MPI level, it's around 1 microsecond. That is kind of a rough ballpark. And large messages, as you see, as the message size becomes larger, then of course uh, the bandwidth, higher the bandwidth, it helps. So in this case, is the Connect X6 SDR is winning here. This slide shows left hand side is the unidirectional bandwidth, and the right hand side is showing bidirectional bandwidth. So here you will see a clear change. Here you can see like this is the QDR. You remember we talked about all those different speeds: QDR, FDR, dual FDR. This is EDR. So like this, you see with every generation of newer adapters, bandwidth keeps on improving. And a similar trend we see it on the right hand side also for bidirectional. Now, if you take a look at the similar like a Infiniband and Rocky, we have similar trend at a low level. If you see, remember 130 nanosecond was different. It is very similar here. So that is being reflected. And one thing to note, in fact, all these RDMA layers we talked about, if you remember, like the Infiniband, the earlier I showed, low level is 730 nanoseconds, and this is 910 nanoseconds. Okay, so that means API layer is able to actually just put a little bit what um, um, 180 nanosecond with a 180 nanosecond overhead. We are able to actually put a software stack on top of hers. Okay, so that shows like how the state of the art libraries are being designed. If an underlying network can give you performance with very little overhead, we should be able to enable it at the upper layer. The bandwidth wise is similar, like a as we saw, like a Infiniband gives a little bit of additional advantage compared to Rocky. So here we go into a 12 gigabytes instead of like 11.4, and bidirectional bandwidth comes very close to each other. So these are some of the Rockport networks. I think they have a different, they call it switchless network. So they don't have a switch, but they have multiple links which you can connect in a different topology manner. So this is our latest release. MFS 2237 actually supports. You have access to these. You can try these. Here you get around a 3 microsecond latency for small message internode. And then the unidirectional and bidirectional, you see around 10 gigabytes per second or 20 gigabytes per second. This is the very latest on Slingshot 11, like this is on the Frontier system, and a lot of other systems are coming up in many DOE labs. So we have actually, we just made a release just a few days back. This is a new series we have started, MFS 3.0, 3 series. It goes through actually Wi-Fi. It also has support for UCX. So now we are able to support, not only we have our own design over verse, but we are able to support also through UCX, Infiniband, Rocky and all, and through open fabrics, we support Slingshot, Omni-Path Express, even Intel's new Ethernet adapters. So like this, you can use actually MFPs to do performance comparison and run your experiments on any system. So here we are getting around like a 2 microsecond latency. These are in the very latest technologies. And the bandwidth wise, here we are able to, so this Slingshot 11 is actually 200 gigabits per second. So here we are able to get, it should be 25 gigabytes per second. We are able to drive very close to that, 24, very close to 24. And bidirectional, it is around like a 42 gigabytes per second. And this is on the open fabrics. We talked about the kernelless network. So they have a OPX provider. So through the Wi-Fi, we are able to actually run it. Below is the Omni-Path actually. The actual hardware is Omni-Path. And as you can see here, we are able to drive it with 1.08 microsecond latency, which is very close to the Infiniband we showed earlier. And then on the Broadcom Rocky also, since it is a Rocky, we have been supporting that for many years. So here MFS 237 is like the Broadcom Rocky, they're 100 gigi. We are around 3.88 microsecond. So so I hope, and again, the unidirectional, bidirectional bandwidth, these are 100 gigi network. So we are coming very close, like a 12 point, it's like a 12.5 you should be getting. So it's around, we are able to go into 12.1 bidirectional instead of 25, we are reaching like 24.39. So we are able to actually deliver very high performance, all these interconnects. So I hope that gives you a perspective. Again, we are just giving some sample numbers. If you have your own cluster, you would like to do a lot of other benchmarking, those kind of things, please feel free to use our MPI libraries and all. In fact, we'll go through some hands-on exercises now. But before we go on, we can do two things. We are coming, I think we have around another 17 minutes left. If there are any quick questions, we can answer now. Then what I can do is we'll formally conclude. If you have some other engagements and all, I don't know how many of you have signed up. So we'll formally conclude. And then those of you who are interested in the hands-on, you can stay. We'll continue to work on. We also have the afternoon tutorial starting at 1 o'clock Pacific and 4 o'clock Eastern. That there we'll be talking about machine learning, deep learning, data science, similar to from my team. Are there any quick questions from anybody here? Hari, any questions on the chat? I am not able
there
to
were a few from Michael and others. I have answered them, Dr. Panda.
Okay. So then let me move forward. I'll just skip for the timing hands-on. We'll get back to it. We are not skipping it. Those who are interested, please hold on. So broadly, if you see, I mean, we just had like a 4 hours, but we have covered like a materials or giving the background for last 25 to 30 years. Okay. So we presented all the network architecture, trends in the cluster, presented background and details of all the different networks for HPC, highlight the main features, gave an overview, and also discuss some of the sample numbers so that you get a feel for where the state of the art technologies lies. But then, as you saw, I mean, this field is moving very fast. A lot of these different vendors. Of course, here we remain primarily on network because it's a hot interconnect conference. But you know, the network is also having a lot of impact on GPUs, accelerators, FPGAs. So that is leading to all new kinds of systems. We'll touch a little bit of those in the afternoon version, especially into the machine learning, deep learning, how the GPUs architectures are taking place. But broadly, you'll see, I mean, this is a very fertile research area. If you are some students and all working in this area, there are many open research issues. They require novel solutions. And we'll be seeing many more innovations coming up in the coming years. And you know, like for the last almost 10 years, we have been talking about exascale. And now we have a number one system, exascale, and now people have started talking about zetascale. Okay, so I think we need to keep that in mind in the next decade. How do we design these networks to really reach that zetascale performance? So with this, I'd like to thank all our sponsors because without their help, we could not be doing all this research and bringing these results to you. But more importantly, these are all the heroes. What we presented here, I mean, these projects, MIP's project, and we have been carrying it out for like 21 years. So a lot of students and staffs have actually come, contributed. So whenever I present this tutorial, my salute is to all of them. Okay. So with this, these are all our pointers. If you have any questions, please feel free to ask us later on when you get some time to take a look at some of these numbers in more detail. We'll also be presenting this. We present these tutorials at many places. We'll be presenting it at supercomputing also. And if you have some colleagues who would like to join that, please ask them to join. And especially in the MHAPIS project, we also do an annual conference. It's called MHAPIS User Group Conference called MUG. In fact, we are doing that on Monday. This Monday, Tuesday, Wednesday, we have a very highly packed program. Might be, Hari, you can post that on the chat. If you are interested, I mean, we have vendors from all over the places. We have a lot of tutorials, keynote talks, 18 invited presentations. So if you are interested to attend any of those sessions, please feel free to register, and we'll be starting that on Monday for 3 days. So with this, let me hand it over to you, Hari. Let's go through the hands-on. And by the way, we are okay to even to spend a little bit more time if some of you would like to stay. But if there are any other additional questions, we can handle it at this time. Any quick questions?
Okay. Satoshi has a question on slide 57. Can we use multi? Okay, sorry, let me first. Sorry, just give me 1 second, Satoshi. Let me go to the.
I'm opening up slide 57. Okay.
So on slide 57, can we use multiple connection reliability in one application? I'm assuming reliable.
Yeah, yes. This is the UDRC slides. Yes.
Oh, yes.
So you can actually create queue pairs depending on our application. You can say this kind of traffic will go through. I will have so many UD QPs and so many RC QPs. This kind of traffic will go over UD, and this kind of traffic will go over RC. In fact, we do that in our MPI library also. Any additional questions?
No, I don't see any more. Thanks for the question, Satoshi. Okay.
Okay. So let's start with the hands-on. Yeah.
Sure. So before I start the hands-on, were folks able to log in to the remote cluster as described here? If you guys have any issues, please raise your hand on Zoom, like the raise hand, the reaction feature, so that I can help you.
Yeah, and especially in this part of the things, because we'll be doing hands-on, we need feedback. Okay, otherwise it is like we are talking to a black hole, right? We'll not know whether it works or not. So please indicate your feedback through the chat, or I don't think they can unmute themselves.
Probably not. So
okay.
Again, show a reaction, or like at least mention it in chat. Like both of us are observing the chat. So if you have any issues, let us know. So assuming the lack of response, I'm assuming everything, like everybody were able to log in. So all we require you to do is copy paste these commands exactly. Okay. So if you look at the file, there'll be a readme.txt. Just open that, and all you will have to do is copy paste it, nothing else. Okay. Copy paste the command just like that. So the first thing that we are trying to do is at the lowermost level, we are trying to measure the basic latency that you can get at the verbs level. So you guys remember verbs? We talked about that in the big slides. So like you have application which goes over verbs, which goes over RDMA, which goes over the user space, and IB switches and IB cards and IB switches, right? So that is the part that we are trying to test here. Okay, the most basic one. And this is the best performance that you can ever hope to get on this particular system. So here we are measuring point-to-point latency, which is half round trip time. So you send, you receive, you measure the one-way round trip time. Okay, half round trip time. All right. So this is a benchmark which does that. So it reports a lot of metrics: the minimum time, maximum time, your typical or your median time, average time, standard deviation, and percentile. So all of these, so this is the 99.9 percentile. So this is what is referred to as tail latency. Okay. So this is the worst time that maybe like 1,000 iterations took. So you run this benchmark for 1,000 iterations and you measure the worst time. Okay. So if you remember back with the discussion about slingshot 11, this was the time, this 99th percentile time was what they were trying to particularly reduce. Okay. So I'll wait for a couple of minutes for you guys to execute this. Were you able to do this? Again, I'll just give a minute or so for folks to try this. And of course, remember that you are running on a shared system. We have like several nodes reserved for you, but you might not see the output instantly because others are also running it. Okay. So again, assuming that most of you were able to run it, we'll now look at some of the different characteristics, so to speak. Okay. Now, if you go back to the previous slides, between like slides about 30 to 45, we talked about different kind of models, right? We talked about your one-sided model, your two-sided model. We talked about write and read and things like that. So you have benchmarks to measure all of these performance characteristics. So send latency measures the two-sided communication. Okay, send, receive, send, receive, send, receive. Okay. Now write uses a different verb called RDMA write, where you use the one-sided semantic to directly write to the application's memory, and read uses a different semantic where we read from the remote memory and bring it back locally. Okay. So broadly, you will be able to see that write has the best performance here. So you see here, and you will also be able to see this from your numbers. So write will have the best latency, followed by your send receive operation, followed by your read. Okay. So this is one trend that you will observe. Okay. Similarly, you can also measure the bandwidth. So latency is like a half round trip time. Bandwidth is like sending a lot of messages back to back and trying to observe how many messages we are able to get through in the shortest amount of time. Okay. So this benchmark measures the peak bandwidth, average bandwidth, as well as the message rate. Okay. Now, depending on the size of your message, either bandwidth could be important or injection rate or message rate could be important. If you are looking at the smaller message spectrum, then it is the injection rate or message rate that is more critical. How many messages am I able to push through into the network? If it is the larger messages, then it is mostly the bandwidth that matters. Okay. So if you run this, if you just copy and run this, we will run internode between two separate nodes. We will run a bandwidth test. Okay. So once you do this, you will see that there could be like a similar performance trend. So your bandwidth increases as your messages increases, and will kind of stop once your link is saturated. On modern networks, we see that your link will typically get saturated with 1 or 2 MTUs. Okay, 1 MTU is a maximum transfer unit. It is the amount of data that can be sent over a network without it having to be chunked into smaller packets. Okay. So as we saw, the MTU for SRD was 8 kilobytes. Remember that? So here for most IB networks currently, and you are running on an InfiniBand network right now, for IB networks, the MTU is around 4 kilobytes. So you will see that around 4 to 8 kilobytes is where your network bandwidth is going to get saturated. Okay, around that area. Well, like 1, 2, 3 MTUs, that's when your network bandwidth is going to get saturated. So that is another trend that you will observe here. Okay. Beyond that, your packets are going to get serialized. Okay. So until you hit about 1 or 2 MTUs, there is enough width in the road to handle more. So think of this as a freeway. Okay. So as long as you have more lanes in the freeway, more cars can go in parallel. But once all lanes are full, then the cars will have to get serialized. They'll have to go one after the other. So that's typically what happens once you cross about 1, 2, or 3 MTUs. So your data is going to get serialized, okay? Because there is no more available road for the cars to go on. So that is a trend that you'll observe here. So now we'll go to the MPI level. So MPI is one step above verbs. So you have hardware. On top of hardware, you have different kind of software interfaces. Verbs is one such interface. On top of verbs, you will have application programming middlewares or applications sitting on it directly. MPI or message passing interface is one such middleware. So all these numbers were taken with the MBAPitch MPI library, which is something that we developed in our lab for the last 20 years, as Dr. Panda mentioned. We just show this because we have the most experience with this, and if there is a question, we can quite easily answer that. The same numbers will be visible with any other MPI library like Intel MPI, OpenMPI, HPCX, anything. Okay. So you will see that if you just copy and paste it, we will be doing internode evaluations. Okay. So again, what you will observe is that your latency and bandwidth and bidirectional bandwidth will look something like this. Another observation will be that the latency that you get at the MPI level will be slightly worse than what you get at the verbs level, because you are adding another software level on top of it, obviously, right? And that your bandwidth, just like on the IB verbs level, increases as the message size increases. Okay. And the latency is kind of close to the IB level latency, but there is still some degradation as expected when you add another level of software on top of the lowermost level. So with this, we kind of come to the end of our hands-on exercises. I'm hoping that you guys were able to run all of these things and execute it. Okay, there is a question from Michael. So does the test switch from the eager to the rendezvous protocol at some point, or is it straight RMA? So for those who don't know what eager and rendezvous is, so eager and rendezvous are two different communication protocols that is used inside an MPI runtime. Okay. So what is eager? An eager protocol is used when you know for sure that your recipient has a buffer of that size already pre-posted to receive this data. Okay, so I can just send it and I know that that guy has like a buffer of that size to get this data. So if I know that, if a message is less than eager threshold, I can just send it. Okay, I don't have to wait for an acknowledgement from the remote process before sending. But the flip side of this is the receiver side has to pre-allocate a lot of buffers. Okay, it has to reserve a lot of buffers to receive data in like potential data in the future. So if you do this for very large messages, you will have a lot of impact on your footprint. So for large messages, what you do is you send a request. Hey, I want to send you so much data. Do you have enough buffer allocated for it? The receiver on getting this message will allocate the buffer and send a response back saying that I have allocated the buffer, go send it here. Okay. So there's a handshake that happens, a rendezvous. Okay, a handshake. So that is why this protocol is called a rendezvous protocol. Now, at the MPA level, Michael, yes, the switch will happen between eager and rendezvous. Typically, we have seen that for most networks, this will happen at around the 8K or 16 kilobyte level. Different libraries choose different protocols. Intel MPI, for instance, sets the eager threshold to 128 kilobytes, which means that till 128 kilobytes, they would be using eager, and after that, they would be using rendezvous. So yes, it does always happen. All MPI libraries will do that. The verbs level benchmarks, on the other hand, don't have this concept. They will do straight RMA because they only have one buffer, which is the communication buffer. They don't have a separate application buffer. I hope that answers your question, Michael. Any other? Yeah, sure. Glad, Mike. I'm glad it helped. Thanks. Any other questions, guys? Were you guys able to run the benchmarks? Any issues that you were facing? Were the trends that you observed similar to what you saw here?
Yeah, and also I think we would like to mention that means all these scripts and all, if you would like to try it on your system and all, you have local system, please feel free to do so.
Yeah, you feel free to copy all of these scripts to your local systems and execute them. Okay, your accounts will be active for the rest of the day, so feel free to do them. Thank you.
Okay, so I think if there are no other questions, I think we are exactly at 3 o'clock here, 12 noon Western. So we covered a lot of material. Sudhir, would you like to add anything here?
Yeah, thank you so much, Dr. Panda and Hari. It was great. I personally learned a lot. This is quite a bit of information. Yeah, thank you all attendees for active engagement. Someone is post a great tutorial with the slides. Yeah, I think Hari already posted the link.
Yeah, so the first one, yes. So the slides are available. Yeah.
Are you able to see my screen?
Yes, yes.
Okay.
Yes.
Yeah, here on the slide itself.
Yeah. I have posted the link to the slides in the Slack channel. So if you go to the top of the Slack channel for this particular tutorial, you will see the slides. I had also pasted them a few times in the chat. Let me do that again. So the slides are here. I'm pasting that again in the Zoom chat.
Maybe we can pin it. See.
Let me. Okay.
Yeah, I did that.
Oh, I think so. Okay, you already pinned it. Thank you, Sudhir.
Yeah.
Okay.
If not anything, yeah, thank you so much, Dr. Panda and Hari.
Yeah, we'll take a break and then come back very soon for the second.
Yeah, sure. Yeah, second one starting at 3 p.m. Central.
Yeah, 3, 12. Sorry, 1 o'clock Western, 3 Central, and 4 Eastern. So we'll be starting. Okay.
Yeah.
Thank you,
Bye.
guys. Then.
Thank you so much.
Bye. Thank you.
Bye.
Bye.
Bye.